Sorry. Good evening. Can you hear me?
Yes, sir. Yes, sir.
Okay.
Shall we start, sir?
Yeah, sure.
I would like to invite Mr. Notalpata Ayyap Garu, Senior Principal Engineer, Marvel Technology, Pleasant and CA, USA, as a session speaker to deliver the topic on network security and advancements in real-time applications. I now request Mr. N. Ayyappa Garu to take over this session, sir.
Sure. Let me share my screen.
Yeah, yes.
All right. Are you able to see the screen?
Yes, sir. Yes, sir.
The big screen, right?
Yes, sir. Yes, sir. Yes, sir.
Okay, cool. Good evening, all. Thanks for joining the session today evening. So today we are going to discuss mainly about the network security and advancements in the real-time applications. Myself, Ayappa Nutalapati. I'm working as a senior principal engineer in Marvel Semiconductors in Santa Clara campus in USA. And let's start the session. This is a quick recap on myself. So I have finished my bachelor's in electrical and electronics engineering in Venkateswara College, University of Engineering in Tirupati. And I have 20 years of experience in the networking industry, and I have a couple of patents. This is a quick intro, and I have my family picture. Moving on. So this is a basic prerequisite for this session as well. Need to have an understanding on the network terminologies and as well as the embedded concepts. It's not a mandatory thing, but yeah, feel free to interrupt me for any questions or any abbreviations or anything that is missing, so that we can have a quick glimpse on what that could be, that terminology or networking concept that we are discussing in each of these slides, so that everybody's on the same page. So before we jump into the network security, we are going to discuss mainly about the classes of network that is typically deployed today in the industry, right? So you see at high level, there is a carrier network. So this carrier network is basically the telecommunications network that is operated by the service providers, which is basically the mobile network that we use today comes under this carrier network segment. And we have the enterprise network segment. This is mainly the private network that is used to by the organizations. Could be an office or it could be a college or anything that they use to connect for in between the departments. So this is like an enterprise network. And we also have the data center network, which we have discussed in detail in the last session, which is mainly used to connect the servers and storage at a hyperscale level. So this classification of these networks has various reasons. It could be a business purpose, or it could be the technology that is varied across all these classes of network, and also the targeted customers for each of these. So there are various use cases that differentiates between these types of network that we have in the market today. So this is a quick comparison between the three different types of networks that we just discussed. If you look at the scale level, the carrier network, we have the nationwide or a global wide, that carrier network that has a connectivity. And in the enterprise network, you'll see it is limited to a campus or a cross campus network, that you will have the organization specific private network, which is not open to the public. And data center specific, which is a network that is deployed in the data center, which have its own connectivity inside the data center, and it will have its own a gateway to the outside world for any connectivity to these data center services that are hosted by these data centers. And the purpose is like for carrier network, it's like the service delivery, like the mobile services that we use today. And in the enterprise network, it's mainly for the internal communication for the organization to communicate between the departments. Data center network is mainly the infrastructure that is hosted in the data center can be used by various applications, right? It could be the applications hosted by the organizations for any cloud services, or it could be a private service provided to the consumers that the data center resources can be utilized by anyone. With key technologies with respect to the carrier network is mainly used is the 5G or 6G that use it for the radio communication, and MPLS and optical transfer network OTN is used for the once the radio is connected to the converted to the Ethernet communication. That's where it uses these technologies for within the service provider network, the MPLS and the OTN networks. And the enterprise network, it uses LAN, local area network, WAN, the wide area network, and the SD-WAN. This is the software-defined wide area network. So these are the technologies that enterprise network could use within its campus. Data center network uses a traditional Ethernet, and it could use a fiber channel as one of the options for the connectivity. And also, it uses software-defined networking. So software-defined networking is a very generic term, but it has various technologies under the software-defined networking. It could use various technologies, as I mentioned, and the main need for this software-defined networking is to control various switches, routers, and servers and storage, which will be hundreds of thousands of nodes that are present in the data center. Needs a centralized control. So that is provided by the software-defined networking today, which is called SDN. And the bandwidth perspective for carrier network, we have multi-gigabits. It's a very high bandwidth that is growing demanded market from 4G to 5G to 6G. The demand for the speed is growing high and high as it comes from one generation to the next generation. And in enterprise network, since it's mainly for the internal communication, it is moderate enough speeds are sufficient for this enterprise network. And for the data center network, it is extremely high. I think we talked about in the previous session on the need for this data center network speeds has grown larger with AI applications recently. With respect to the latency, which is nothing but the time it takes to complete any task, right? So, and the time it takes for that packet to travel from source to the destination. In case of carrier network, it is expected to be moderate enough to get the latency, and in enterprise network, these are like going to run some business apps, so it needs very low latency, and data center ultimately needs the ultimate ultra low latency that is needed for the data center network. From the ownership perspective, we talked about it, right? So it's like basically the carrier network is for the service providers, the enterprise network is for the campus organizations, data center network is mainly for the hyperscalers. Irrespective of this type of networks that we just discussed, network security has been playing a pivotal role with the recent technologies that have been developing at the same pace. The threats or attacks to this kind of network has been significantly growing day to day, and the need for network security has become very key. Plays a key role in the network security. Why do we need network security? There are various reasons why we need network security today, and pretty much most of us know already about this, but I just try to cover at a high level. The key points why we think that we need this network security is the first one is data protection. Of course, the information that is being sending over this network is very sensitive. It might contain there's some intellectual property, or it might contain some financial data information, like you'll be sending some bank transactions, or you'll be sending some customer information on the wire. So protecting the data is highly important, and we cannot leak it at any cost. And also the business continuity. So since in this the modern world, there is nothing that is hosted at the native server, right? So people are trying to access everything on the mobile phones, which is accessed through the cloud, which means that the people expected to have the services to be continuously available. So any disruption in these services because of the cyber attacks will cost a lot. So it is always highly important to prevent any disruptions that could be caused because of any DDoS attacks, cyber attacks. Is highly important for the business to make sure that it should be always remain online and functional. And the next reason why we need network security is the compliance part of it, right? So the data privacy. So at any point of time, when we send anything on the wire, it's not just we worry about getting attacked. It's all about even the privacy, right? Anything that has been communicated between the source and the destination, the expectation is that anybody else should not be reading the data that is being sent over wire. So data privacy and security has become a key reason that network security is playing a key role here. Financial impact, yes. So it's huge cost, right? So if we are talking about the daily trading, so or bank transactions, all such things are happening online, and any such attacks on those transactions will put on a hefty cost, and can happen because of any data breaches if the network security is not in place. So now that we know why we need network security, there are various elements that play or come into picture in network security today. I have listed a few of them here. It's not limited to these key elements. There could be more than this, but at least I was trying to cover at a high level what are the basic infrastructure that is needed for network security to be to keep in place. So if you look at the firewalls, so firewalls is like mainly used to filter the traffic and block any malicious activity. These firewalls could be placed anywhere in the network topology. And the access control. So we have a traditional and most popular used AAA that is available in the market, which is basically provides your authentication, accounting, and authorization. So which means you will not get access to any of the network resources unless you are an authorized user to access. It could be accessing a network switch or a router, or it could be accessing a server, or it could be accessing any resource. So you has to make sure that the access control is in place for any device that has been placed in the topology. And the intrusion detection system and prevention system. There has been need for this monitoring tools has been becoming getting a higher demand, considering the lot of attacks, the DDoS attacks, and the malware attacks that happens in the recent times. That these intrusion detection tools has been playing a key role in the network monitoring. Anti-malware software, yes. So this is the endpoint software that will be helping on the end hosts to detect and remove the malicious attacks. Data encryption. So data encryption, there are various technologies for which the data encryption is possible today. One such technology is SSL, which is used to encrypt the data during the transmission. So this is highly important for data privacy. So this has become very common today. You take even a WhatsApp messages today has been going through the data encryption, which could use one of these technologies. Network segmentation. So you need a software to segment all the networks such that you classify the network and you monitor the traffic patterns flowing in the network is highly important in the network segmentation. if the monitoring the traffic patterns will really help you to understand if there are any suspicious flows and if you need to enforce any security policies. All those things are can be kept in place with this network segmentation technology. So we are going to discuss little details about this network segmentation and how we are going to achieve with the software-defined segmentation with multiple other infrastructure that is available in the network security market today. If you look at a typical network security monitoring architecture, there is a quick high-level diagram that I have put in here. So you could see these routers that is already in place for a traditional networking, like for the traffic to switch or route. The packets will be going through this primary router or secondary router to connect to the cloud or internet today, which could be hosted in any of the classes of networks that we just discussed, right? It could be a carrier network or a data center network or enterprise network. So you will see commonly the routers being deployed or the switches being deployed in the network. And in those routers, typically, if there is a need for this network security monitoring, the corresponding business or the type of network will be placed with additional infrastructure, which you could see here, starting with taps. So this tap will help you to sniff the traffic over the wire. So any traffic that is going over this wire will be sniffed and then sent to a router. It could be sent to a network packet broker. So the highlighted version here is the network packet broker. So the tap traffic will be sent to this network packet broker, and this network packet broker will decide on sending to these web monitoring tools. So these monitoring tools could be used for each tool could be used for various applications. As we discussed in the previous slide, it could be doing a firewall, it could be doing an intrusion detection system, it could be doing some encryption. So these tools has grown a lot in the recent times, but at the same time, these tools needed some additional network infrastructure that it can get the traffic that it needs to monitor the traffic such that it can produce efficient results. So that's why this TAP and network broker and packet broker plays a key role in the current network security monitoring infrastructure. So getting little zoomed into that network infrastructure that we saw in the previous slide, the TAP. So this is a test access point. So this is an actual hardware, which is not a switch or a router, but it's a box that is placed on wire anywhere in the network. So you just place that box, and every network port, you see in this case, you see a network port A, network port B. For every network port, you will see a corresponding monitor ports. Like a traffic coming on A will be monitored, sniffed on monitor port A. Traffic coming on network port B will be sniffed on monitor port B. So those sniff traffic can be sent to the monitor device directly from this network tab today. So this network tab can be placed anywhere in the network today. So this is the basic device that is being deployed in the current data center world or anywhere that needs not any additional technologies, but just to tap the traffic and send it to the host or a monitoring device will be can be achieved with just a basic network tap. So it's a hardware device setting in the network segment, and it accesses and monitors the network traffic, and it needs as many monitor ports as it has the network ports on that router or switch. So if you need to monitor only 2 ports, then you need a 2-port tap to sniff the traffic and send it to the monitoring tools. So another block that we were looking at in that topology before is the network packet broker. So this network packet broker brings in another infrastructure technology that is installed to filter the traffic that is received from the tap and organize it before you send it to the security tools. The reason why we need this is there could be various flows that it be tapped from various ports, and those ports could be sending the same duplicate traffic, or it might need some filtering on based on the application for each of the monitoring tool, might need only certain flows that needs to be monitored. So all those filtering cannot be done at the monitoring tools, because the monitoring tools are mainly software based. So you need a proper hardware based network packet broker which can help you filter this, aggregate it, replicate it if it needs the same traffic to be sent to multiple tools. All those functionality can be achieved through the network packet broker. So this will help you effectively monitor the data across the network to produce better results. So the key points about this network packet broker. So the first key thing that it can achieve is the traffic aggregation. So basically, you could install taps across the whole network wherever you would like to have it, and all those taps can be aggregated to a single network packet broker or more than one, if you would like to, and that will help you to aggregate all the traffic from multiple tap points that has been installed in the network, and this can do the aggregation part of it. And it will do filtering and distribution, which means basically it can let you apply some policies and filter it based on various traffic parameters like protocol, IP address, MAC address, or any application level information based on TCP, UDP. All those traffic related parameters can be used to filter the patterns and redirect them accordingly to the monitoring tools that are connected behind this network packet broker. It would also help the monitoring tools avoid unnecessary data to be delivered. Like the firewall traffic is expecting certain traffic, you just only filter them and then send it to those firewalls, whatever the traffic it is expecting. Similarly, for the intrusion detection system or the data loss prevention system, each tool that are connected behind this network packet broker is dedicated for a specific use case. And the goal is to filter these packets at the use case level and then redirect the specific traffic flows to that corresponding traffic monitoring tools. And it will provide you the improved security results. So because you are making sure the tools receive the right data here. And it will also help you to do a load balancing, which is basically if you are having let's say the intrusion detection system, and the traffic receiving for this intrusion detection system is a huge traffic that a network one tool cannot handle that much amount of traffic, then you might be deploying multiple intrusion detection system tools behind this network packet broker. And this network packet broker can help you replicate the traffic load balance the traffic across these tools so that it is not oversubscribed, and it will help you to load balance across those network monitoring tools that is sitting behind this node. So the previous architecture that we just saw in the previous slide, where it has again topology, where it is doing a tap and then sending traffic to the tools, which is called the out-of-band network packet broker, where you are sniffing the traffic and you are filtering it, aggregating it, filtering it, distributing it to the tools, which is basically an out of band, which means that the original traffic will be still going from router to router or switch to switch, but the sniffer traffic is basically a copy of the traffic that has been sent to the tools to do an offline analysis. And also there might be certain use cases where you don't want do offline analysis. You want to do the traffic analysis like on live, which means it's doing the in-band, which means basically you wanted to analyze the traffic which is flowing on the wire from router to router or switch to switch. You don't want it to delay anything, right? Like, let's say if you're doing a financial transaction, if the transaction has some issue and if the traffic has already gone to the destination, and you try to sniff it and then analyze it, it might be too late to react. So in such cases, the expectation for those few kind of use cases is to use in-band network packet broker, which means in this case, you will install a bypass switch, and the bypass switch is going to send the traffic, the data traffic coming from the internet, send it to the network packet broker, and the packet broker will be doing all this aggregation, filtering, load balancing, helping you to send the packets to the monitoring tools and make sure those packets are well and good and authenticated well enough that these are valid packets. And once it is treated as to be a genuine packet, then you could send it back to the network such that there is no possibility of threat or attack that has happened for any such transactions in the deployed networks. So, which is basically the in-band network is called like a bump in a wire, which is basically that any traffic that's going between router to router, you are having a bump, which means you are redirecting it to some other network monitoring infrastructure, having it analyzed and sending it back. So this provides the security for live traffic and take any immediate action that's needed, right? But only downside for this is that you are adding a little latency to the traffic flow, because you might be analyzing something and then it might take some extra cycles before it goes back to the wire. So this could add latency. So you need to have a compromise on whether you wanted to have a latency is compromised, then you can use this in-band network packet broker. Otherwise, you might always wanted to use the out-of-band network packet broker for security monitoring. And also, it needs the inbuilt failover capability, because there is a possibility that tool might have a failure or link might have a failure. In that cases, you don't want the actual live traffic to have any disruption. So there are certain hardware features or software features that are available today to make sure that the failover is handled immediately for any such live traffic. If the tool has a failure, you'll immediately take the bypass switch will take care of sending the traffic directly on wire without sending it to the security monitoring tools. And also, if the traffic that is being exchanged between the source and destination and the live traffic is an encrypted traffic, right? So this in-band tools need some key exchange, because if the traffic is already encrypted, you will not be able to decrypt to analyze unless you have a key that is being used to exchange that encrypted data. So the packet brokers or the tools might need the actual key to decrypt this data before they analyze the traffic patterns that is being flowing on wire. So the use cases for this packet broker. So we talked about the firewalls and IPS and IDS, the intrusion packet detection system, and any detection leaks. And also the packet broker will help you control the cost, because you can manage remotely, and you will be able to do a load balance at line rate across multiple monitoring tools. And you are getting a real-time network performance, which is basically a line rate handling of all the traffic that is flowing through between the routers or the switches. And also, these packet brokers has brought in a lot of application intelligence, where you could understand a little bit more than what a layer 2 parameters are, what layer 3 parameters are, what type of application it is. Is it running some WhatsApp application, or is it running some HTTP web application? So those kind of intelligence is also needed to understand on how those packets can be redirected to the corresponding tools for it to be analyzed. And these network monitoring tools will also use to analyze any traffic drops, right? There could be some drops happening in between, and this infrastructure could be used to analyze any drops that have been happening in the wire. So we will be talking mostly on the on-premise, which is basically the native on-wire network monitoring tools. But in the current trend, the applications are not running natively on any servers. So it has been running on the cloud, right? So if the applications have been hosted on a cloud, you might want to install these network monitoring tools into the cloud environment as well. So if your services is hosted in AWS, or it's in Azure or in Google Cloud, you might want to install virtual tabs, like similar to the hardware tabs that we discussed in the previous case. You might install a virtual tabs that could be tapping the traffic from each VMs that hosting those applications, and these virtual tabs will sniff the traffic, and then collect them, aggregate them, and then send it to the traffic monitoring tools for its further analysis. You could see here a picture that depicts on the left hand side the traffic that is being tapped from the virtual cloud. On the right hand side, you will see the on-prem, which is the hardware traffic, that actual hardware tap point that is installed between the routers or switches to tap the actual traffic with the physical tap points. So this is a hybrid multi-cloud network monitoring tools also are available or being deployed these days to tap both the virtual VTAP virtual traffic environment in environment as well as the on-prem environment where you might want to tap the traffic. SPAN is another technology that's been widely used today for traffic monitoring. SPAN is basically like switch port analyzer, which is also referred to as another term called port mirroring. So this does not need any additional boxes like a network packet broker, or it does not need a tap point, but it can use an existing port in the switch itself to send the traffic to the monitoring tools. So if you have, let's say, 100 port switch, you might use out of that 100 ports, you could use 10 ports to enable this SPAN, which will basically trying to mirror the traffic going from the going in and out of the remaining 90 ports. So the main advantage is like you don't need any additional tap hardware. At the same time, you are going to reduce the cost by utilizing the existing switch, and only thing is that you might have to sacrifice some of the ports on the existing switch, and you try to configure the existing 90 ports which are being used for the actual live traffic can mirror to these 10 ports that are connected to the network monitoring tools. So, and the SPAN can configure to add any appropriate header to differentiate on which port. Like you could use, let's say, you could use VLAN, right? So you could add additional VLAN on each of the packet that is being sniffed. So if it is coming in and out of the port 1, I could add VLAN 1 and send it to the SPAN tool, so that the SPAN knows that the network monitoring tools knows that it is the traffic that I'm been analyzing based on the traffic that's received in and out of the port 1, so that it knows where the traffic has been received and what traffic has been sniffed and what traffic has been sent to the monitoring tool. That will help you analyze and take any action for any anomalies or the unusual detected traffic patterns. There has been some advancements in this SPAN that are available today. The basic SPAN does the basic mirroring, which is you basically saying that any traffic that comes on this particular port, you just send on port 1, you just send it to this port 91. So just send all the mirroring traffic. So that's how it has been done with the basic mirroring. In case of remote SPAN, so this can be used where the monitoring tool is not directly connected to the switch where you are monitoring the traffic. So where you might have to add a VLAN header or some additional reserved fields to the existing packet, so that this SPAN traffic can be sent over the existing network, such that the monitoring tool that is residing somewhere remotely across after multiple hops, this VLAN header will help you to redirect the traffic over the network and reach the right monitoring tool for the traffic to be analyzed, which uses this RSPAN or the remote SPAN. And we also have the further advancement here is that the ER-SPAN, which is basically the encapsulated remote SPAN, and there are multiple types in this again, which is like a ER-SPAN type 2. So which is like a little advancement for this existing RSPAN, where instead of adding a VLAN header, you might be adding a tunnel header. Like in this case, we are using a GRE, which is like a generic routing encapsulation. So instead of adding just a VLAN, you could add a total additional IP header and a VLAN, MAC, and additional data that you would wanted to insert in this ERSpan type 2 headers. So that will help you to completely encapsulate the whole traffic flow, so which cannot be used by anybody else, because as soon as the traffic is being spanned or mirrored from the original traffic, you add this ERSpan type 2 header, and that becomes altogether different packet, because the whole original packet becomes the payload, and this ERSpan type 2 header will help you to construct the tunnel header, which could construct an IP or layer 2 header on top of it, that can be used to redirect the traffic anywhere in the world that you can send it out. And further advancement to the type 2 is the type 3, where you could add some timestamp on what time that I have sniffed this traffic, that can be embedded into this ERSpan header. And also you could identify, you can add some more additional parameters, like on which port or which destination port, which source port this traffic has been sniffed on, that can be added into the header itself. And then you could add even the switch IDs where this traffic has been sniffed, or and that it can flow across multiple switches, so can be encapsulated in the ERSpan type 3 header as well. So there are a lot of details for this, but just at a high level, these technologies has been keep on evolving based on the use case or the demand, the requirements that keep coming in. People try to contribute to add more and more to this, to the network security tools, whatever the data that it might be expecting. So these headers keep getting advanced. So the next topic that we're going to discuss is the ACLs, which is basically called the access control list. So this access control list has become a key component, which is like an inbuilt component in the hardware for any switches today, part of the forwarding pipeline, that is highly helping the network security requirements that has been coming up recently, right? So this ACLs is basically means that it tries to install a set of rules to filter based on the traffic parameters, because you don't want to filter the traffic at the software level, that at the CPU level, to parse the packet and find out where the MAC is, where the IP is. It is very difficult to handle such huge line rate traffic, like if you're talking in gigabits or terabits level of traffic, cannot be filtered at the software level. So that's why the need for this ACL technology in the hardware helps you filter all these traffic patterns, whether at the layer 2 level to filter on the MAC, VLAN, port, or you would like to filter based on the IP address, which is the layer 3 parameter, or you wanted to filter based on the layer 4 parameters based on TCP representation. It could be beyond this layer 4 as well if you wanted to filter based on some application level traffic. So it's some information based on some HTTP information or some SSL information. So if you wanted to derive any bit on the packet, so these ACL or the access control list rules will help you filter at each bit and byte level. So the technology it uses is the ternary CAM technology. It's a specialized memory that goes into the hardware, will let you filter at line rate at any bit and byte level. So you wanted to filter only, in case of IPv4 address today, we have 32 bits. Out of 32 bits, you could say that I wanted to filter only the first 16 bits or first 8 bits of that traffic pattern. Then you could filter only on certain bits, and then you could filter on those network parameters and take corresponding action. You might wanted to permit the traffic, or you think that it is a suspicious traffic that you wanted to deny, because you don't expect such traffic pattern on this wire. So you know that it will be only this certain traffic patterns that you are expecting, and if you are seeing something else, then that means you wanted to deny such traffic, or you wanted to meter that such traffic, which because maybe it's not a highly important traffic. You think that this IP address based traffic is not a highly critical traffic. Maybe I need to meter it, limit it to certain bandwidth, or maybe it's a very high important traffic. Then I need to give a high priority to it. So all those corresponding filtering and corresponding action could happen at line rate using this ACLs today. And it could also do replication. So you wanted to send the case where we talked about if the same traffic has to be sent to multiple network monitoring tools, then I could use the replicate technology in the ACL level to to send those traffic flows across multiple traffic monitoring tools. And as I mentioned, based on the vendor capability, it can run at line rate or on a switch router or on a networking route. I mean, ACL as such is a technology that you could use at line rate for any on the hardware, but it doesn't mean that you should not do it on software. Software can also implement. Software has any capability. So if anybody wants to do it at the software level, they can still do the similar technology at the software level. Just that you cannot run at line rate there. So the next section we're going to talk is the on the same lines, the data security or the privacy, right? So one other technology that is being widely used in the market is the IPsec, where this is mainly used for the secure connection over the IP network. Particularly the financial transactions could use this IPsec technology, where you will be encrypting the data and you add authentication to it so that only the end host understands how to decrypt that data that is being sent over wire. So this IPsec technology basically scrambles the data that is going inside the packet. So if anybody is trying to tamper it or try to sniff it and find out what is happening on that packet, it will be very difficult to find what it means unless the source and destination is the only person guys who will be knowing what that traffic means, because they'll be exchanging a key, a private key or a public key that they will be exchanging between those end hosts. That key will help them to encrypt the data or decrypt the data, over which they will be able to make that scrambled data to unscramble it on the end destination so that it knows what that traffic means. So this IPsec is a kind of widely used technology for all the financial transactions today. So this IPsec is another kind of like an encrypted tunnel, as is depicted in the picture on this right-hand side. So you will see it's being used widely today for data privacy by scrambling the data inside the packet. SSL, the secure socket layer, or TLS, is another technology that operates at the application layer. The one that we discussed in the previous slide, the IPsec, operates at the layer 3 level or the routing layer. The SSL operates at the application layer. So this is a widely used at the applications today, like HTTP is a non-secured one. The HTTPS is something that we look at as encrypted SSL encrypted communication that happens, right? So this is something that we usually notice when we open a browser, and you'll see if you are trying to do any financial transactions or any such doing any payment methods, you will look at this HTTP versus HTTPS, which tells you are either on an insecure connection or an encrypted connection. So if you're going through the HTTPS, which means it's an encrypted connection, and it uses some SSL certificate to encrypt the data from the user to the remote server, wherever the connection has been made, so that at least it cannot be tampered or it cannot be breached. The data cannot be breached anywhere in between. Right? So this encryption has been widely used today in multiple applications. So the authentication happens only between the endpoint devices, and the data integrity is highly important today, right? So that it cannot be tampered by anybody in between before it reaches the actual recipient. the applications of real-time systems. I think at a high level, we've been talking as we went through multiple slides, but there have been many sectors today, and the demand for this network security has been growing in day to day, right? So think about the telemedicine that we are trying to do all real-time monitoring by installing multiple biomedical devices that has been used by the consumers that have been remotely sent. The data has been sent over the wire to the healthcare doctors or anybody who is monitoring these vitals of the consumers. And if they are doing any remote surgeries, so all those things need the data privacy is very important, and also you cannot have any hampered traffic getting hampered or getting breached will cost a lot in the telemedicine area. And also the autonomous vehicles, right? So we've been looking at the advancements happening in the autonomous vehicles today. So people are the market in the autonomous vehicles has been gone to a level of self-driving, where the accuracy and the probability of happening a mistake happening in these autonomous vehicles should be close to zero. So, and any mistake happening in those cases is highly unacceptable in our autonomous vehicles sector. Online gaming is also becoming more popular, and that has been consuming a lot of bandwidth. At the same time, that is a growing business that that is pushing for a huge demand on the network security as for today in the online gaming. Of course, with the financial systems, that's a given that they need these network security monitoring tools, and the latency also plays a huge role that that they cannot compromise on any transactions taking time before someone hampers it or there is any intrusion that has been detected on such transactions happening on the financial sector. So the importance has been mainly enforced on protecting the data, and also we make sure that there will be the services uninterrupted. So you cannot handle such cases like medicine, healthcare, or autonomous vehicles or financial transactions. Any of these things will not adhere or will not withstand any disruptions happening for those applications in real time. The advances in the network security technologies, going beyond the market has been adopting the AI and machine learning to study the traffic patterns that is happening over the network over the period of time, so that any new patterns or any new anomalies detected can be easily identified if these networks has been enabled with AI and machine learning. And also the models that has been deployed in this network security today has been zero trust. You cannot trust any such traffic pattern. You have to verify each and every flow to make sure that there is no possibility of mistake happening here. Blockchain is another technology today that has been highly used in the cryptocurrency. That is also like very highly secure and tamper-proof transactions that can happen in the blockchain. That has been widely started with crypto, and it has been used across various industries now as well. The other one is the quantum cryptography. That's also like like Unbreakable, which is like an encryption that is using the quantum mechanics. This also like has a very strong secure communication using the quantum key distribution. These are like very highly advanced technologies that has been getting evolved to aid the network security, help and avoid such intrusions happening in the network. And SaaS is another technology that is being widely used for network security in the campus network, where they have been deployed with WAN or SD-WAN kind of technologies. Key takeaways: data protection is highly important. There is no doubt about it. And the architectures that we discussed needed multi-layered approach, which means the packet brokers, taps, the virtual taps needed to be installed at various levels, and these packet brokers will help aggregate it, filter it, aggregate it, filter it, and distribute to the various tools and help defeat the threats or intrusion detections at various levels before it is kind of like past where the transaction has been completed, before it's too late. So it has to be detected as soon as possible. So the way that can happen is to do the regular monitoring. You cannot just have periodic wings. It has to run all the time. Like the network bandwidth that is being used for the network security is as equal to or even more than the actual bandwidth that is used for the live traffic today, because any vulnerability that happens cannot be taken at any cost. So this regular monitoring and updating the tools and the tools to react way ahead before the damage has happened is highly important to make sure that the network that is being deployed is secure and safe. That's pretty much from my side today for this session. Feel free if you have any questions. I'm going to end the show, live slideshow, and see if you have any questions.
There is a question. How about security of virtual networking?
Yeah, virtual networking, as I mentioned, the applications or services has been widely deployed in the cloud today. There is not like a native applications are not being widely deployed these days. It's everything has been deployed on the cloud. Considering that the TAP or the packet brokers that has been already used in the native world has been moving to virtual as well. So these virtual taps, virtual mirroring, and the virtual packet brokers are being installed close to the VMs. Like it could be a Docker, or it could be a container, or it could be a VM, so that you snip the traffic or monitor the traffic flows at the VM level and detect any anomaly that happens in advance. Any other questions?
Other question, what is mean by algorithmic trading?
Algorithmic trading, I think this is mainly on the financial sector side, that is mainly used for the trading market today, which happens by not with a physical person, right? So it's like there are multiple theories and algorithms that are available in the market today to monitor the particular trading, right? Like if you are looking at Google, or you're monitoring particular stock, the algorithm trading technologies like Wyckoff algorithm. So all those things will be run by the AI kind of like applications to monitor the pattern on how the trading, like buying or selling happens today, is done by the AI applications, and corresponding sell and buy transactions also happens automatically from the consumer account. So these algorithmic trading, which is widely used based on the trading technologies that have been deployed today, needs this network security to make sure that there is no data that has been tampered on that application, to make sure that the buy and sell of those stocks happens in a secure way.
So there is another question.
Yeah.
Generally in India, we'll have a more number of transactions are doing with the help of UPI. Hello.
Yeah, I can hear you.
Yeah. So most of the transactions nowadays, from the past around 1 or 2 years, we have been doing transactions under UPI. It's a unified payment interface. So almost from the middle class, low people, I mean, anyone, most of them were nowadays is dependable on UPI. So there are few cases that even the transaction has been taken up from from sender to receiver, there is a chances that it is been holding some time. A transaction would be failure. What would be the cases, whether it is been a failure of network or it is been from the sender, from where these could be the errors would be occur? Is there any specified reason is there for the transaction failures?
It is hardly to say if there is one specific reason where a transaction could fail. As I mentioned, end of the day, detecting this anomaly of the traffic patterns is just based on the various traffic parameters that it uses on the flows, right? Think about like the IP address that it is using for doing a particular UPI transaction. Say you're doing it from your home, connected to your Wi-Fi, and then you are doing it with a particular IP address, and it knows that particular geographical location. Say you are in Tirupati and you are doing this transaction, and it knows that the transaction originates from this Tirupati location, happening with this particular bank that you are trying to do either deposit money or transfer money that you are trying to do. All of a sudden, you try to send it to move to a different location, or you've been traveling and you're trying to do something else. So, and you do the similar transaction with a high amount, then it is considered as a traffic anomaly, right? The pattern is not usual. If you are trying to run this kind of like AML use cases, applications, it thinks that, okay, this pattern is not expected from this geographical location. So it might signal the banks or the any financial institutions saying that something is not correct. So, and then that might trigger either to go for additional scrutiny, like you might be getting an OTP, or you might be asking a call from the bank to say that, okay, there is an unusual thing that is happening. And then they might hold you the transaction, or they might ask you to reinitiate again, right? So this is just one of the reasons, but there could be n number of reasons, right? The whole point, what I was trying to say is that if in this case it could be a genuine transaction, but there could be a case where your phone has been tampered, and then somebody is trying to initiate the transaction from a different city with your same phone number or with the same IP address, or for the same UPI ID. So then it's easy for them to block it than allow it. So in those cases, it does happen that you might have to redo it again, or make sure that the bank releases it before it happens, right? So, but again, so the network security is in place, and that means that it's working that enough to make sure that the trust transactions are monitored.
There is a question from other participants. Data security can be measurable with any parameters. Why? Because many times data is hacked by others.
Can you repeat again?
Data security can be measurable with any parameters.
Of course, the data security can be measured with any parameters, right? It depends on the application. It depends on the layer. If you look at the networking layers today, right, you have the OSA layer or the layers, TCP/IP stack. You could be detecting an anomaly at any layer today. So it doesn't need to be restricted to one particular IP address or a MAC address, or even the application level TCP or UDP sessions that you are trying to run, or it could be the HTTP session, or even it could be a transaction that you're trying to make on WhatsApp. So the data security cannot be measured with certain parameters based on the application, the monitoring tool that is being deployed, and the use case can enforce demand the requirement to filter the anomalies at any layer. So it could be n number of parameters. Few of them we already discussed in the slides, but it depends on the use case today.
Another question. Can you discuss about security challenges facing by networking?
Security challenges. security challenges basically that what we see today is the latency, right? That's the major security challenge that we face today, because if we are trying to analyze the traffic that is being on wire, and if it's a financial transaction or a trading transaction that happens, if you are trying to analyze something for the anomaly and the transaction that you're trying to make it on a trading stock, you might be missing the price that you were trying to buy or sell for that particular trading transaction. And having security on top of it poses a challenge that you are affecting the latency there. So that's one of the huge thing that that the current market is trying to address, to make sure that at any cost the latency cannot be compromised. At the same time, you will not have any compromise on the security as well, that you don't want the transaction to be hampered or triggered by someone else than the actual consumer. So that has been slowly getting improved by using the in-band network packet broker, one of the technologies that we talked in one of the slides, right? So those network packet brokers is trying to make this latency to be reduced as much as possible by doing enough traffic analysis on the line rate itself before sending it to the tool, such that the transaction gets finished at the minimum latency time, and at the same time there is no compromise on the security as such for that particular transactions.
So, more question. What types of data sets are typically required for training AI/ML models in network security?
The models, again, this depends on the use case, but at least to my knowledge, it's mainly the traffic flows, right? So if you ask me, I will be in my experience, it will be looking mostly on the traffic parameters compared with the geographical locations. Is a basic data set that you might be wanted to feed it to the AI/ML model to say that, okay, you are expecting these traffic flows or patterns for these applications for a given user, right? So that kind of data set or parameters that you might be feeding into the AI/ML model to know that the usual traffic patterns that is expected from a DEN device, and anything different from it will flag a warning for it to either analyze it or feed it to as it as a new data for it, or did that as an anomaly and raise a flag. So in the network security world, so that's been an evolving technology now. Since AI/ML models itself for the existing live traffic is just happening, right? So for developing on top of the network security is a newly evolving industry that's happening now.
So one more question. How can reinforcement learning can be applied to optimize firewall configurations?
To optimize the firewall configuration. So in the current technology or the current industry, in the current deployments, right? So it is highly difficult to do any configuration on any of the device manually, right? So you don't want the network administrator to go sit on a firewall and configure the rules or edit the patterns, and then and then say that, okay, filter this, allow this, block this, meter this. So those kind of rules, applying it on the firewall is highly difficult to do it manually by the network administrator. So that's where most of the firewalls, as I understand, is coming up recently with zero touch configuration, which basically means you're just going to connect the firewall, power it up, and then connect the wires, and that's pretty much it. And it needs to be fed firmware, either from the upstream router or the tool that is connected behind. She will let you feed all this firewall to be what needs to be configured based on the location of the deployment that is happening. Will let you feed that configuration dynamically so that it helps you scale faster and flexible enough as you move this firewall to a different places. And all these network equipments, whatever we just talked about, right? It could be a firewall, or it could be a network packet broker, or it could be a tap. All of this has been initially used to be the dedicated hardware, and going in the cloud and virtual environments, this has become virtualized as well, which means that these virtual firewalls or virtual taps or virtual packet brokers has been not anymore running on dedicated hardware. So those are running close to the VMs that can help you instantiate the configurations dynamically based on the use case and the deployment that happens there.
So is there any specific frequency band for the network security, or is there any limitation that is to be only applied for these networks, or any for communications? Is this any specific frequencies are there, or?
If you're talking about the radio frequencies, yes, there are certain ranges that people use it that are reserved for the experimental purpose and or even for this anomaly detection purpose. At the same time, you could also embed that information into the packet, which tells you that this packet is not a regular forwarding packet. This is a tap traffic or a sniffer traffic by using the headers that we just talked about, right? The span header, span header. So those additional headers that are encapsulated on top of the existing traffic flows will let you identify that this is a monitoring traffic that needs special handling compared to the regular live traffic. So that's how the traffic has been, the monitoring traffic has been differentiated from the regular traffic for network.
There is a question from Abdul Khadir. Good evening, sir. Could you tell us if there are any weak spots in networks that other try to enter through into network, and any measure that we can take to recover them?
The main thing that could easily happen in the network world today, like is the authentication, right? So the authentication, like basically accessing your network, right? If you are trying to log into your own router that you have at home, right? So it's easily able to be logged in with the default passwords, right? So that's the easy spot or soft spot for the hackers to log into your switch or router. Could be it is on the consumer level or enterprise level, right? That needs strong authentication, right? So which is deployed using this AAA, the authentication, authorization, and accounting technologies, which is complemented with certain network protocols like 802.1x. So there are certain radius .1x radius protocols which will be communicating with a remote servers. So there are dedicated authentication servers that are being remotely placed, which is not for the consumers at least, but for the enterprise world or data center world, there will be dedicated authentication servers. So when somebody is trying to log into a network switch or a router or a tool, so they will communicate or send a transactions, the AAA transaction using this 802.1x to the remote authentication server to make sure that you have the right person with the right authority to make such modifications. If somebody is trying to change the configuration, if you are not allowed to such thing, so you will not be provided such rights, right? Only the admin, network administrator might be able to have all the admin rights to modify the configuration, to filter the traffic or redirect the traffic or however it wants to do. So this authentication with complemented authentication servers will help you protect the network, which is the easy way to hack by the hackers today.
Thank you. And there is a question that how can we manage network security?
How can we manage network security? That depends on the use case. If you're talking about a network security at talking about a home laptop, that we are just doing it with multiple malware software that we try to install today, which does monitor the applications locally installed in the software versus the same softwares has been enhanced to detect the traffic right on the network port itself, right? The traffic that is receiving itself has been monitored before it is processed by the application. So those tools will help you to detect any malicious or attack-based applications that are trying to bring in onto your laptop, right? That's at the consumer level. Looking at the enterprise level, we need more sophisticated infrastructure, right? So that's where we bring in this tabs, packet brokers, span, all those with monitoring, special monitoring tools that are being deployed behind the network than the actual network. So these monitoring networks plays a huge role. I know that it costs a lot for typical deployments, but it's worth it not to have any disruption or any other attack can happen based on the industry or the use case where those networks has been deployed.
Sir, question, in what scenarios would RSpan be preferred over span? That's a question.
So span is basically basic mirroring, which means any traffic that's coming on port 1, you just send it to port 2. It just any traffic that's going in and out of it, or you can control only the in traffic, not the out traffic, or only the out traffic, or both in and out traffic. You can say span it or sniff it and send it on the other port of the switch. That's the basic span traffic. But the sniffing on port 1 and sending it on port 2, and if the monitoring tool is directly connected to the port 2, then it's fine, you can have span, right? What if that monitoring tool was not able to connect on that particular switch itself? What if it is that a monitoring tool is connected 2 or 3 switches behind, or maybe it's connected in a different domain, that you wanted to send the traffic over the network, this monitored the sniff traffic from port 1, you configure RSpan, where you could add a VLAN header, which could be a reserved VLAN header that you wanted to use it, which is not conflicting with the existing VLANs that is used for the normal forwarding, right? So you dedicate a specific VLAN for this monitored traffic, where you use the RSpan technology and add a specific VLAN header on it, and that VLAN will help you to redirect the traffic where the monitoring tool might be residing multiple hops down the line, where the tool is actually connected. So that's where you use RSpan over span.
There is another question. How do AI and ML differ in their applications for network security?
So AI and ML complements to each other as such today, right? So the machine learning, when it comes to the network security, you are basically studying the traffic patterns across the whole network, right? So it need not be studying a particular switch or a router or a segment, right? You might be analyzing the traffic pattern over the whole network. If it is a campus network, you might want to monitor the whole traffic patterns happening across multiple nodes, including the host, right? So this ML will help you feed all the data that you need, right? And complementing with AI, you are going to take any such actions if there is anomaly detected, right? So it needs a lot of parameters for the AI to take some action, and machine learning is going to help you to feed the data that is needed, and AI can take action in the network security. Again, this is the evolving thing that's happening now, but yeah, so but there is a lot of scope to improve in the AI ML complementing the network security today.
Dear participants, still anyone have any queries you can ask? Harish sir, I think no questions
Yeah.
are raised.
Participants, do you have any doubts you can clarify with the expert, or else we can wind up the session? Okay, I think so. No response from the participants, sir. I think so. All the doubts have been cleared. Thank you, sir. Thank you, sir, for clearing all the doubts by the participants. And I would like to express my heartfelt thanks to Mr. N. Ayyappa garu for providing a comprehensive overview of network security and embedding in the industry. So the topics you have covered, like classes of network, elements of network security monitoring architecture, and applications in the real-time systems. All these topics are very helpful for our faculty community, such that it can be delivered to our students, and as well as it can be involved in our curriculum also. Thank you, sir. Thank you for your session.
Yeah, thank you, Harish garu. Thank you, Dilip Kumar, and thank you, Sunita garu and Pushpalata garu, for providing this opportunity. It's nice to meet you guys. I hope this session is going to help you a lot.
Sir, thank you, sir. Ayyappa, sir. We enjoyed a lot, sir, with your 2 sessions.
Yeah, thank you.
Ayyappa, sir, thank you
Yeah.
once again, sir, for interaction also, for clarifying our doubts.
Yeah, thank you. Thank you so much. All right. Yeah, thank you so much. Thanks a lot.
Yes, sir. Thank you, sir. Yeah, bye.
Bye.
I request all participants to stay for 5 more minutes, that our session 2 expert will join the session.
So by the time I request all the participants, kindly fill the feedback form, which is to be posted now. Kindly wait for a few seconds, it will be posted.
Dear participants, please submit your feedback, which will be posted in the chat box. Some of the faculty members individually asked feedback sessions, but it is not possible to send each and every person. Please try to understand our problem. So that will be posted in the chat box. You can submit in the chat box. Thank you.
Okay, madam. Thank you, madam.
Sir, a message from Nagaraja, sir. The exam will be on the last day, sir. The material corresponding to all these presentations will be uploaded in the Atal portal. I think so. The participants individually can download the material such that the questions will be from that material only for test. Thank you.
Kindly check feedback link in the chat box, all the participants now. Harish, sir. HOD, madam, am I audible, madam?
Yes, madam. Yes, madam.
Good evening, madam, HOD, madam, and coordinator, sir.
Good evening, madam. Naveen sir yet to join, madam.
Okay, madam.
Yeah, hello, am I audible?
Yes, sir.
Sir, you are audible, sir. Good evening, sir.
Yeah, hi, madam. Yeah,
So good
Good
evening,
evening,
sir.
sir.
good evening, madam. Yes, yes.
It's my privilege to introduce Dr. KP Naveen Garu, who are truly honored to extend a warm welcome to Dr. KP Naveen, an esteemed associate professor and head of the department at IIT Tirupati, a distinguished academic and researcher. Dr. KP Naveen has made remarkable contributions in the fields of performance analysis of wireless networks, network economics, game theory, and optimal control, and many other cutting-edge domains. Dr. KP Naveen holds a PhD from IISc Bangalore, India. And Sir had worked at the ISRO Satellite Center, Bangalore as a scientist C. And also, Sir has published many papers in IEEE elsewhere and Springers. I now request Dr. KP Naveen Garu to take over the session. Thank you, sir.
Yeah, so thank you for the kind introduction, and also thanks to the organizers, HOD madam, and all the faculty colleagues there for inviting me. So happy to be part of this FDP program. So let me share my slides. Yeah, I hope my slides are visible.
Yes, sir.
Okay, right. Yeah, so the slides are visible. Yeah, so the topic is on wireless communications. I mainly come from the wireless communication background, mostly performance analysis of wireless network. Okay, so I'll mostly talk about the communication aspects. So particularly, so this is going to be the outline. So what I will do is first I am going to in detail talk about 5G. And the other very important technology, so that's the Wi-Fi, right? So both of these technologies are coexisting with us. So I'm going to talk about these two, okay? And then so next is I'll talk about the particularly 5G specifications and so on. So just a second. Yeah. Yeah. Okay. So I assume, yeah, slides are visible, right? Clear. Huh? Okay. Yeah. So 5G and Wi-Fi technology. So that's what I want to talk about. So, so specifications of 5G we'll look at in greater detail. And also I talk about Wi-Fi. So if I want to talk about Wi-Fi, first we should understand what is meant by unlicensed band. So we all use Wi-Fi very extensively, right? But we also need to understand something about the unlicensed band. And then I'll talk about how these two can coexist together, okay? So generally, I also talk about mathematical models, coexistence problems, some optimization problems, something related to game theory. For this talk, I'll mostly focus on the experimental study that we have conducted. So using something known as USRPs, right? So USRPs means Universal Software Radio Peripherals, or the other terms, popularly known term, is the software-defined radio. Okay, so I'm going to talk about software-defined radios also, how we conduct some experiments using SDRs. Okay. Okay. So first let's try to understand why we need 5G, right? So we are all happy with 4G, right? We all been doing live streaming, gaming, and so on. But why do we even need 5G? Okay. So what we see is once 4G was introduced, so the demand for data has been continuously increasing, mobile data, right? So these days it's all mobile data. We never switch on to TV as well, right? Live cricket, And also these days, the phone call is never audio calls, right? We just go for video calls and so on, right? And gaming is very popular among the student community, right? So all these are all live gaming, so these are requires heavy bandwidth and so on, right? So with the advent of these newer and newer applications, so we need more and more data, right? So in fact, Cisco does a lot of research in this direction. So they publish a report known as the annual internet report. So this is slightly outdated. The numbers will be much bigger than what you're seeing here. So over 70% of world population is already having internet subscription, smartphones, right? So this number is very big. So 5.7 billion is what we are talking about. So we are generally used to lakhs and crores, right? So what is 5.7 billion? So 5.7 billion is essentially 570 crores. Okay, so I have mobile internet subscription. And it's not just these applications that we are talking about, right? In future, we are envisioning more and more data intensive applications. One is IoT. So you would have heard of IoT, right? Internet of Things and machine to machine communication. Okay, so already some of the IoT enabled devices you would have purchased at your home, right? So you can connect it to the Wi-Fi. So smart home applications are already started. Okay, and also smart driving is something we are talking about. Okay, so whenever suppose you buy a car, it comes with something known as the ADAS feature, right? So advanced driver assistant features and so on. So all these will run on mobile data, right? Many things will require mobile data. So the newer cars will also be enabled with some radar features and so on. So car to car communication and so on. Okay, so a lot of applications are envisioned. And also industry 4.0 or industry 5.0 newer ones, right? So machine to machine communications, right? So everything will be connected. The entire industry is going to be automated and so on. So this is going to add to the data requirement that we already have. Okay. So again, the Cisco report says that the machine to machine devices is expected to grow at 30%. Okay. So it's going to be much more than the smartphone devices. So there'll be more machine to machine devices than the smartphone devices in the future. Right. So it's clear that we need more data, right? And also we need, so it's not just data, we need a network that can support a varied varieties of applications, right? It's not just now phone calls or video calls or live streaming. There are much more newer devices introduced into the cellular network, right? So you need a new type of network that is going to support these features. So now first let's try to understand what is 5G, right? What is 5G? We have been hearing about these things, right? 4G, 5G. 5G is already there, but I'll tell you how it is different from the original envisioned 5G. So we still don't have the complete 5G network deployed, right? So I'll tell you how by the end of this lecture, so you'll be able to know the difference between the deployed 5G and what is the true idea about 5G. Okay, so I'll just take you. It's good to recap about different generations of cellular networks that we have come across. So early 1980s, the first generation of networks was deployed, and it was mainly for analog voice, right? Voice using analog communication. When I say analog voice, the analog communication, and we have missed this era, right? So not much. Yeah, so we had these telephones, right? So long distance calls we used to make and so on. So that's the first generation. It was purely based on analog communication. And you know that analog communication is more prone to noise, right? It could just support voice calls, right? And moreover, it was something known as the circuit switch network, right? Circuit switch. So there used to be an operator, and generally you used to speak with an operator, and operator will connect you to, you will switch you to different networks, right? So that's how the first generation worked. Then the early 1990s, from analog, we switched to digital communication, right? So essentially, digital voice was introduced, and we were using something known as CDMA, right? You had heard about these terms, CDMA. So I'll briefly talk about CDMA also later. So code division multiple access. Okay, so that was the second generation communication, and again, it was only limited to voice calls. Okay, so that's second generation. Then let's see what happened. Third generation. Okay. So this was somewhere around 2000. So you see, with each of the generation, the mobile phones, okay, so with the complexity of mobile phones, right, the features of the mobile phones also were increasing. So that means it's not just communication, it's the electronics and the embedded systems. So both go hand in hand, right? So communication was known long back, even in 1950s or even late 1970s. People knew about all digital communication techniques, but there are no electronics to support that communication, right? We need fast, high-speed electronics, right? So with the advancements in electronics and embedded systems and VLSI, right, it was possible to implement the sophisticated algorithms in communication, right, developed in the area of communication. Okay, so 3G, now they started looking at mobile data, so voice calls plus mobile data. So the version of CDMA known as CDMA 2000, and we started getting data rates of the order of kbps, right? So someone who started using telephones in mobile phones in early 2000s, it was not very popular. Early 2000s, I still remember, it was not very popular. But we used to get some data rate of the order of kbps. So that was something possible, right? It essentially for you can news articles you could read, but of course, internet was still not so popular there. And somewhere around 2005, so mobile phones started penetrating the Indian market, right? So 2005, I was in final year of my BTech program, and I remember only one fellow student had a mobile phone in the entire college. So it was so sparse, and suddenly in the span of 1 2 years, so mobile phones, right? So mandatory to have mobile phones. So everyone started having mobile phone. So 3G, it started from 3G, right? The mobile phone era essentially started from 3G. Otherwise, it was a luxury item. So very selectively people used to have, right? Even telephone connections or so the mobile phones, so very selective. So from 3G onwards, it started penetrating the Indian market. So then the real revolution happened when the fourth generation was launched. So fourth generation was about, of course, voice calls and then as well as data rates. Now some useful data rates we started getting. Mbps, okay, so million bits per second. And it was, the standard is known as, so 4G or LTE, they popularly called as long-term evolution. And there we switched from CDMA to something known as the OFDM. So I'll talk about OFDM also, orthogonal frequency division multiplexing. So that was what enabled us to increase the data rate significantly, right? So the fourth generation was all about data rate, right? Now, what is fifth generation? So 2020 onwards, now it's deployed across in India. So fifth generation is not just about mobile data, mobile broadband. So it's also supporting something known as machine-to-machine communication and low latency application also. Okay. So 5G, we are expected to get data rates of the order of gigabits per second, right? So in some prime areas, you will be able to get data rates of this order, right? So theoretically, gigabits per second is possible. Okay. Then fifth generation is also expected to support applications that require very low latency, right, of the order of milliseconds, right? Suppose if you want to do remote surgery and so on, you need very low latency, right? Because the hand movements of the surgeon or the doctor should be captured in the order of milliseconds. The surgeon might be sitting in the hospital, right, conducting an operation remotely, right, with all the equipments, and the patient might be in some village who is in some hospital kind of setup. So the latencies are expected to be of the order of milliseconds, right? And the reliability should be high. So whenever surgery is happening, the connection should not get disrupted, right? So high reliability. So massive network capacity, right? So now we are envisioning every device to be connected to the internet. So you really need to have very large network capacity and availability. So it should be available, right? So seamless availability should be there, right? So these are the essential features of 5G. Okay. So again, so these are, again, I'll talk about the specifications. So there are essentially 8 specification requirements of 5G. So as I talked about, right? So the data rate is expected to be of the order of 10 gigabits per second right now. So in 4G, it was of the order of 10 Mbps. Now we are increasing by 10 times. okay, or 100 times in some locations as well. Latency of the order of 1 millisecond, right? So this, 1 millisecond latency is crucial for some applications, okay? And the bandwidth, right? So large bandwidth. So we should be able to support large number of devices and varied variety of applications, right? So up to 10-year battery life for low power IoT devices, okay? So whenever you have some IoT devices, you should not worry about charging or changing the battery, right? So this is important. So that means whatever IoT devices that will be deployed, okay, their battery life should be large. So that means we should come up with algorithms or protocols that will ensure that they don't drain away their battery. Short packet communication, right? Large number of devices, but very short messages, right? So IoT devices need not transmit lot of data, so very short messages, right? So that's also envisioned. So this is also part of Industry 4.0, where large number of small devices will be connected, okay? So then network energy usage, right? So people are always talking about green network, green energy and so on. So you don't want base stations that will transmit huge amount of energy, right? You want small number of small base stations, low energy transmission, right? So that's reduce the energy usage also. So that's also part of the 5G requirement. Of course, not everything is possible to implement. So trying still work is going on in this direction. So they call about 100% coverage, right? So people are coming up with innovative ideas to increase the network coverage, right? So in US, they are talking about, so in remote locations, you want to have coverage. So they're talking about some drones flying over some remote areas to ensure that the coverage is available even in very remote areas as well, right? And of course, availability, right? So almost all the time it should be available. So there should not be any disruption. Okay. So these are some key 8 specification requirements of the 5G network. And also let's look at the usage scenarios, which I was talking about, right? So this is what makes 5G different from 4G. 4G was all about mobile broadband. 4G operated somewhere here, right? Of course, mobile broadband is important. We want to continue to have our live streaming, right? Video calls, live gaming, and so on. So we now call it as enhanced mobile broadband because we are increasing the broadband capabilities, right? So from the throughputs from 10 Mbps to 10 Gbps we are talking about now. So enhanced mobile broadband. But the other key feature is massive machine type communication. Okay. So machine to machine communication. So this is particularly useful for Industry 4.0, smart automation and so on, right? So you have an house, all equipments are connected to your 5G network, right? So remotely you can check the status of your washing machine, fridge, okay, and AC and so many equipment. So that is massive machine to machine type communication, right? People are talking about smart cities, right? Where the entire, so in fact, Tirupati is identified as one of the smart city, right? Okay. So all the lighting system, everything is connected to the 5G network, right? So these are all possible if we are able to have a network that can support large number of connections. So that's what is massive machine type communication. Then the other key aspect, see the triangle. So this point of the triangle is about ultra reliable low latency communication. So this is what I was talking about, remote surgery, right? Ultra reliable. There are 2 things here, latency, reliability, right? Highly reliable, very low latency means delay, right? When you send a message in milliseconds, right? So the message should reach the destination. So ultra reliable, low latency communication. So this is also one of the key aspects. So now self-driving cars, right? So self-driving cars has to continuously communicate with the base station to know there are cars in front, you should know the traffic conditions and so on. So these applications of this form will require very low latency, very reliable communication as well, right? And so right now the 5G network that has been deployed across is mainly focusing on enhanced mobile broadband. Now people are talking about something known as 5G-B, which is 5G beyond. Okay, so they're going to introduce this low latency communication or M2M communication aspects also into the 5G. They call it as 5G beyond. And people are also talking about 6G, where artificial intelligence also will be incorporated into the cellular networks. Okay, so a lot of activities are going on in that direction. But right now, whatever 5G you get is all about enhanced mobile broadband, right? But uh, but you can imagine the kind of newer and newer applications that's going to come up once 5G or 5G beyond has been fully deployed, right? So someone from 20s would not have believed that if someone told that you can watch TV over a handheld device. Okay, so that was unimaginable, let's say in late 90s, right? So no one was able to imagine. So even in 2005-6, right, when we had mobile phone, it was just for calls, right? It was just for audio calls. No one could have imagined that it was possible to even watch TV, live TV, right? Not even recorded TV, live TV. So that's important, right? So no one would have imagined, right? So now standing at 2025, you cannot imagine the kind of applications that's going to come up in next 1 decade or even in next 5 years, right? So people are talking about augmented reality and so on, right? So it's possible with more bandwidth, it's possible to have a workshop or an FDP of this form where we are sitting in some virtual environment, right? And I can just make a presentation. It's as if we are in some auditorium setting, right? So we cannot imagine the kind of applications that's going to come up because of the advancement in cellular technology and the mobile technology. Okay, so a lot of it's a very interesting era. So a lot of newer and newer applications, advancements are going to happen because of 5G and 6G technology and so on. Okay. Right, the key takeaway is this one. So 5G envisions to connect virtually everyone and everything together, including machines, objects, and devices, right? So everything will be connected to the network. Of course, a lot of security issues will be there, but 5G is a very reliable network. Okay, so cyber security, right? All aspects have been worked upon, right? If you look at literature in the area of 5G, so you'll find all varieties of work happening, right? Starting from cyber security to enhanced mobile broadband to URLLC, machine learning in 5G, and so on. Okay. Yeah. So these three, the three triangles or the three vertex of the triangle that you saw, three kinds of applications. The challenge is their requirements are completely different. Okay. So in the case of enhanced mobile broadband, the important part is mobility, right? So one important part. So we require high mobility. So you are on the flight. So you are in train or you're in a bus, right? So or driving. So you need so high mobility, right? So the mobility feature has to be high. Of course, spectral efficiency. User experience is very important. Enhanced mobile broadband, right? So you have live streaming. So you don't want any disruptions in between, right? So requirement is high. So the way to this is known as a web graph. So a graph of this form is known as a web graph. So the way to understand this is look at these circles, right? So this says what kind of requirement is there, high, medium, and low. The inner triangle represents that the requirement is low, right? And there are three webs here. One is the blue web. Blue web is about enhanced mobile broadband, right? So look at the where it touches. So that says that what kind of requirement is, so each of these specifications, right? What requirement is there for these different kinds of application, right? So data rate should be very high, traffic capacity high, network efficiency is also high, right? And let's go for machine to machine type communication. So the connection density has to be high. Whereas for enhanced mobile broadband, the connection density requirement is medium, right? Because there are not many devices as compared to the population, right? There are more devices than people. So that's why machine to machine type communication, right? The connection density requirement is very high, right? In a home, if you take in a family, so there are like 2 adults, right? 3 or 4 adults, right? But the number of devices will be of the order of 10 or 20, right? So that's why there'll be more devices that are connected. So machine-to-machine communication requirement is high, whereas they are all stationary devices, right? So their mobility feature we don't worry about, right? Spectrum efficiency, so there's nothing like user experience data rate, right? So they're all short packets that are being communicated. So you need not worry about the requirement is very low. Data rate requirement is also very low. Okay. So that's one feature about the machine-to-machine type communication. And ultra reliable low latency, again, mobility is required, very high mobility is required. Latency requirement, of course, is very high. Rest of the specification requirements are going to be low. And see, latency and mobility, right? So think of one application where you are operating a drone remotely. So let's say we are sitting at Tirupati, and let's say there is drone at some remote location in Bangalore or Delhi, and we want to operate the drone, okay, or UAV using sitting in Tirupati and using only the 5G cellular network. So I talk about drone, not a rover or anything. Drone, because you need to give controls, right? The delay should be of the order of milliseconds. Otherwise, the drone, so if the delay is of the order of even 50 milliseconds, so the drone might go out of control, right? So very high latency requirements are there, right? And mobility requirement, because the drone is continuously moving, so you need high mobility requirement. So you should be able to operate the drone over the 5G network on the fly, right? And now you can imagine the kind of applications one can come up with, right? If you can remotely operate these devices from remote locations, so a lot of novel applications. So novel startups are going to come up because of 5G and 6G networks and so on. Okay. So that was some motivation for the 5G network. So let's also try to understand some technical specifications of 5G. So 5G has something known as the new radio. So they call it as the NR frequencies. So it's going to operate at two main bands, frequency bands. So one is known as the sub-gigahertz band. So 3.3 to 4.4 gigahertz. So the 4G networks were operating at megahertz band, right? Somewhere around 900 megahertz and so on. And also another band has been opened up for the 5G network. So millimeter wave band, which is like greater than 24 gigahertz. So this is fully not operational, but once this is operational, so you can think of microcells and picocells, right? So your respective campus might have a small 5G network of its own, right? Very small cells, base station installed at the terrace. Okay, so these are known as microcells and picocells. Okay. So that's possible with millimeter wave, okay, the short range communication. Then the other key feature of the 5G, or which makes 5G to achieve the required throughput, is massive MIMO, right? So massive MIMO stands for multiple input, multiple output. So it essentially talks about the number of antennas that your device is going to use. So it's going to provide additional spatial dimension for increasing spectral efficiency. More antennas, you can transmit more data. So now, so we already have MIMO, right? Your Wi-Fi or even your mobile phone has multiple antennas, right? So of the order of 4 or so on. But with massive MIMO, we are talking about 64 transmit and 64 receive antennas, right? Which is roughly 5-fold increase in capacity, which is going to yield. Okay. Then also, multiplexing techniques people are talking about. See, OFDM we already had. So orthogonal frequency division, multiple access. So this is essential for achieving enhanced mobile broadband. Then also people are talking about NOMA. So non-orthogonal multiple access. So this is mainly required for URLLC and massive machine-to-machine type communication, right? So non-orthogonal. So these are kind of communication where it can so it's like VIP messages that can bypass all other messages. So it will be given high priority, non-orthogonal. So it need not wait for any channel. So whenever there is a very high priority message, so it will just be transmitted by halting all other messages, right? So essentially that's something about NOMA, but a lot of activities are going on in that direction also. And another key feature is operation in the unlicensed spectrum also is allowed. So right now, the cellular networks, right? So the whatever base station, so it cannot transmit in the Wi-Fi band. Wi-Fi has a separate band. We'll look about that also. But operational in unlicensed band also is allowed. Okay. So in remainder of this talk, so I'll mainly will look at these two aspects. One is the OFDMA, orthogonal frequency division multiple access, and what is meant by operational in the unlicensed spectrum. So these are the two aspects that we will mainly look at. Okay. Right. So first is I will talk about the OFDMA. Okay. So orthogonal frequency division multiple access. So before we try to understand about OFDMA, let's try to recall something that we already know. Okay. So you might have heard of terms like TDMA and FDMA, right? So time division multiple access and frequency division multiple access. Okay. So let me try to understand these two using this diagram here. So this is the time frequency diagram. Okay. So time is along x-axis. I've plotted frequency along y-axis, right? So frequency is what you need to transmit your data, right? So anything you want to transmit will occupy some amount of band, will require some amount of band, right? So what will happen in time division multiple access, right? So there are, let's say there are 4 users for simplicity, right? So user 1, and this is the available bandwidth, right? So it could be of the order of 20 megahertz, right? Within 20 megahertz, you can transmit whatever data you want. Okay. So 20 megahertz bandwidth is given. So in time division multiple access, the user 1 gets to use this 20 megahertz, the entire block of 20 megahertz for some amount of time, right? So let's say of the order of 100 milliseconds. Okay. So after that, user 2 will get to transmit for the entire so the remaining, so one slot of time, right? User 2 going to use the entire bandwidth. Okay. So user 3 then gets to use the entire bandwidth and user 4. So this time division multiple access. So in contrast, we have frequency division multiple access. So here what you will do is this 20 megahertz of bandwidth that you have, you partition it into 5 megahertz, right? Blocks of 5 megahertz. And allocate each of these blocks to each of the users for all time, right? So that means user 1 can transmit at all time using this 5 megahertz, right? It can transmit using 5 megahertz for entire amount of time, right? Uninterruptedly. So similarly, user 2 can transmit, user 3 and user 4. So all users can transmit simultaneously, but using a lower bandwidth, right? So which is beneficial over other? So you cannot say both are equivalent, right? So both are equivalent, both have pros and cons, right? Because here you are getting a higher bandwidth, but for a shorter amount of time. Here you are getting a lower bandwidth for a larger amount of time, right? In some sense, both are equivalent, okay? Of course, both in time division as well as frequency division, so what you need is you need something known as a guard band, right? So frequency time at least is okay. You can ask user 1 to stop abruptly and then user 2 can start transmitting. But when it comes to frequency, you cannot abruptly ensure that your message ends here. Okay, so some kind of guard band is required, right? So that whenever you transmit some data, right, in one band, it has some energy, so that energy should not overflow into the other bands and so on, right? So frequency division will require something known as the guard band. Okay, right. So, but these both have limitations. So it's not suitable for wireless scenario, and the resources are going to be inefficiently utilized, right? For instance, let's say in wireless scenario, users come and go, right? So sometimes you'll be browsing, you'll switch off from browsing, okay? So another user might come and so on, right? So there's no fixed number of users, right? So suddenly, let's say user 3 is out of the system, and let's say you had allotted some amount of time, so that time resource goes waste. And similarly, in FDMA, so this resource will go waste. Okay, so inefficient utilization of resources. So in view of this, people came up with something known as CDMA. So a lot of activity. CDMA mainly came because of military applications. Okay, so code division multiple access. So what you can do in CDMA is you can So all users can transmit at all times and using the entire bandwidth, right? All users can transmit. But at the receiver end, so there is a transmission. Look at this red transmission. So if you want to decode this red transmission, so you need to have a code to decode that red transmission, right? Code division, right? So if you want to decode the blue code, you should have the respective code and so on. So that way, only the respective transmitter and receivers can decode the messages. So this is known as code division multiple access. So this mainly was used in the military, because military you need to have very secretive communication. So there you cannot do any time division or frequency division. You just have to transmit. So even the enemy transmitter, even the enemy army also will be transmitting in the same band, right? You cannot put any restriction in a war zone, right? But you should be able to decode your message, right? And it should be coded. So that's where CDMA came into picture. And they started adopting CDMA also into the commercial cellular networks, right? So it was successful for a good amount of time. But the problem with CDMA is its performance start degrading as the number of users increase, right? So you cannot get orthogonal codes, perfectly orthogonal codes as large number of, when there are large number of users, right? So that's why with CDMA, we are able to just do voice calls, not too much of bandwidth was possible. Okay, data rate was not possible, right? So this was one key limitation of CDMA. Then lot of revolution happened once OFDMA was introduced, right? So orthogonal frequency division multiple access. A lot of theory on this one, so I'll not go into those things. I'll just give a high level picture of what or how OFDMA operates. So what they used to do, essentially frequency and time or partitioned into something known as the resource blocks. Okay. So although I'm showing it very simply here, there are a lot of things involved here. So there's something known as the cyclic prefix code. So some DFT is involved, inverse DFT, all those things. So I'll not go into those details. But at a high level, you can think of frequency and time partitioned into different blocks. Okay. So there's so many blocks here. So I can allocate the required number of blocks to each of the users like this. Right? It need not be in any, it can be in any random fashion also, right? So I need not be very organized like this, and user requires so many blocks. I can allocate blocks, right? Orthogonal frequency division, right? So all the red users can get different blocks here, right? And also, let's say user 3 is out of the picture, right? So you can allocate or distribute those blocks to the other user, right? So it's very flexible, very fluid, right? So blocks are available, you just have to allot. And even if you lose some blocks, lose some amount of resource blocks, it's a small resource that you are going to lose in comparison with TDMA or FDMA. Of course, even in TDMA, we can try to do the same thing, but it's kind of going to be an unfair scheme, because see, you cannot assign this entire block to or distribute this across different users, right? So whereas here you can do an even distribution, right? So once an user is out of picture, so the smaller blocks, so I can just distribute it to different users. Okay, yeah. And the other challenge is going to be something known as multipath fading in wireless scenario, where what happens is, so there's something known as a concept known as fading, right? Because of which some frequency and some time slots are going to get affected, right? So let's say there is a fading across this time slot, so this entire block is going to get affected. Similarly here, right? Whereas in OFDMA, right? So different blocks undergo different fading, right? So you need not worry much about fading here. Even if there is fading, so all users are going to affect it. Some blocks are going to affect it. It's not going to affect them drastically. So that's something about OFDMA. So with this, next what I will do is I will proceed to something known as the unlicensed band, and I'll mainly talk about Wi-Fi here, right? So if there are any queries with respect to 5G, I'll be happy to take up now. Right? So are there any queries with respect to 5G communication before I proceed to Wi-Fi? Okay.
Yes, sir.
Yeah. Sure. Yeah.
Sir, in 5G communications, which is efficient, that is utilization of frequency for 5G is, I mean, sub 6 gigahertz or else millimeter wave communication, sir. Because
Right.
I
Yeah.
heard that millimeter wave is having a more abstraction would be there for short range of communications. Sorry, for long range of communications.
Yeah.
So loss also would be there.
Yeah.
So sub 6 is more efficient for or else millimeter wave is more efficient, sir.
So both have different use cases actually. So sub 6 gigahertz, you can use the existing cellular base stations with sub 6. So what we have deployed is sub 6 gigahertz. So the millimeter wave has a different use case. So with the existing cellular base station, which has the range of the order of let's say 100 or 200 meters, right? Or even more sometimes, right? So your millimeter wave is not going to work. So for millimeter wave to work, you need to have something known as the concept of microcells and picocells, right? So millimeter is also going to have a lot of use cases, but right now millimeter is not deployed, right? So both should go hand in hand. So one will not replace the other, right? So in some scenarios, as I was mentioning, right, in a institute setup, so you can just have a millimeter, so microcells, more spectral efficiency, but this will be small range base stations. Okay? So millimeter wave, we don't see it in the Indian context. So we just have the sub gigahertz band now, but both are going to be useful. Any amount of spectrum is going to be useful. Okay, so if you want more data rate, you need to have more spectrum and more antennas. So already we are reaching the limits, number of antennas 64, right? So if you want to increase the bandwidth, we should have more, increase the throughput, we should have more bandwidth. So whatever bandwidth is given, we have to efficiently utilize that. So both are going to be useful. So it's not that one over the other. So both will be very useful. Okay. So any other queries?
Thank you, sir. There is a query from Abdul Kader, sir.
Sure, sure.
Will you please tell us why we have the highest speed in 5G? It is due to the wave that we use or just due to the bandwidth?
It is bandwidth and also multiple input, multiple output. Okay. So see, it's like earlier we used to have 4 antennas at the transmitter end, right? Now at the base station, we are talking about 64 transmit antennas, right? So that means so many bits can be transmitted. Many more bits can be transmitted easily. Okay. So that's the advantage of having more antennas. Okay. So the techniques are same. OFDM was still used in 4G, but now we have more bandwidth, also more antennas at the transmitter end. So that's why we are able to get speeds of the order of gigabits per second. Okay. Yeah. Okay. So any other queries? I think it's in the chat box, right? Yeah.
Yes, sir.
Yeah. Yeah.
So
Please
there is another
differentiate
question.
between. Yeah.
So please differentiate between 5G NR and 4G LTE, sir.
Yeah. So 5G new radio. Okay. So as I mentioned, LTE was operating at 900 megahertz bandwidth, right? And also the amount of bandwidth that was given was less. Less means it was enough for getting throughput of the order of 10 Mbps, right? But 5G is going to operate at a different bandwidth, 3.3 to 4.4 gigahertz, right? The bandwidth also given is more, and the number of antennas also are going to be more. Okay. So these are some 2 major changes with respect to 4G and 5G. The other major changes are 5G is expected to support newer types of application, ultra reliable low latency, right? With the old LTE network, you cannot expect low latency as well as reliability. Sometimes call connections will be lost, right? So you cannot expect latency of the order of 1 millisecond. 1 millisecond is a very small latency, right? So it's very important. Okay. So these are the 2 major changes from why 5G, from the differences between 5G and LTE. Okay. LTE or 4G is same, right? LTE stands for long-term evolution, right? So 4th generation long-term evolution, right? So then we are in 5G. Okay. Fine. So any other queries?
No other queries, sir. Kindly proceed.
Yeah, thank you. Okay, so we have now talked extensively about the 5G network. The other technology, highly prevalent, but which is always in the background, which is taken for granted, is Wi-Fi, right? We take Wi-Fi for granted. So let's say whenever we go out to a conference or let's say new institute, we'll always ask what is the password for Wi-Fi and so on. But as communication engineers, we should understand how Wi-Fi works. So it's a very interesting operation involved or interesting algorithm that runs in Wi-Fi, right? Wi-Fi is completely different from the cellular network. Okay, so we'll see how it is different. So before that, let's try to understand what is unlicensed spectrum. Okay. Okay. So what is unlicensed spectrum? First is the licensing is essential to limit interference in certain applications, right? So mobile cellular. So licensing is very, very important, right? So Airtel or Jio or whatever network, right? So they have to participate in the license auction, and then you have to you can only then you can use that spectrum. You cannot just start transmitting. You cannot just have your own cellular network and start transmitting at some frequency. Okay, it's illegal and it's an offense, right? So licensing is required. Mobile cellular network. Okay. So even TV transmissions. So TV transmission happens in some frequencies. So earlier it used to happen when we had analog TVs and so on. So now it's always it's dish TV, satellite communication, right? So whenever you put a dish TV, so satellite is going to communicate to that dish, right? And that uses also some frequency. See, any communication requires electromagnetic waves operating in some frequency. Okay, so earlier TV television. So people from 80s will be able to relate to this. So we had those analog TVs, right? So the box TVs, and if you see, there used to be big towers, TV towers in some cities. Okay, and it had range of the order of hundreds or 100 kilometers. TV towers, so very huge TV towers, right? So they also used to operate in some frequency bands. Okay. Then FM transmissions. So you hear about 92.7 megahertz or 93.5 megahertz, right? So also or FM 93.5 FM, right? So that essentially that number means what is the center frequency at which they are operating. Okay. So 93.5 FM means the center frequency is 93.5 megahertz, right? So FM transmissions. So again, you have to purchase that band and then only then keep operating in that band. So similarly, air traffic control, right? So in airports, you will see there is something known as there is a very strange tower, right? So a long tower and a disc at the top, right? Every airport will have. So that's known as the ATC, air traffic control. So there are people there, controllers, and they communicate with the pilots in the flight, right? So that also happens at some specific band, right? So it's different from your mobile band, but still for safety purpose, you are asked to switch to the flight mode, right? Just so that unwanted energy doesn't go into the ATC band. So you will see that sometimes you might have forgot to switch off, right? So not a still it's okay, but because it's operating in the completely different band, right? Air traffic control. Similarly, military and the police also use these walkie-talkies. So these are all licensed band, right? Licensed means a specific user only can transmit in that band, right? So licensed band has to be purchased, right? You cannot just like that transmit in any band, right? It has to be purchased. It's exactly like real estate, right? So if you want to build a house, you have to first buy a piece of land. You cannot just go and build anywhere, right? You have to buy a piece of land, exactly like real estate, and it is far more expensive than real estate. Okay, so spectrum auctioning is far more expensive. Okay, so then real estate licensing is very, very expensive here. Okay. So as I mentioned earlier, it is an offense to transmit in licensed band. You cannot see building a transmitter and a receiver is very easy. All you need is a mixer and an adder. Okay, so it's very easy to build a transmitter, but you just cannot transmit in the licensed band. Okay, and in some cases, even receiving in the licensed band is considered to be an offense, right? So you are not expected to build a transmitter and receive some military signals and so on, right? So these are considered to be offense. Okay. I think there are a couple of questions. Let's see if there is okay. Okay. Yeah. So I hope the slides are visible, right? Yeah.
Yes, sir. Visible, sir.
Yeah. Okay. Okay. So this is about license spectrum. But licensing is not practical for all scenarios, particularly short-range applications. For example, when you buy a wireless mouse that you connect to your PC, right? You are just buying the equipment. You are paying for the equipment, right? So it operates in some band. So it's an unlicensed band, right? So your neighbor also can buy a mouse that operates in the same band. So there's going to be some interference. So we have to live with the interference. And anyway, these are all short range applications, right? So similarly, cordless headset and base unit, Wi-Fi also operates in unlicensed band, right? So you see, you just buy the Wi-Fi access point for your home. You don't buy that license spectrum, right? So you just buy the Wi-Fi access point and you can just install. You just pay for the device. You don't pay for the spectrum. So Bluetooth, right? So Bluetooth headsets and so on, right? RFID, drones. So these all operate in the unlicensed band, right? So these are short range applications. So there are some long range applications also. Something known as the amateur radio, ham radio, right? So ham radio essentially operates using something known as dot and dash, and this operates at the kilohertz range. I'm not going to talk much about this, but just want to highlight that there are still, so using ham radio, you can communicate with astronauts in International Space Station, right? So this is like low bandwidth communication, you see, so it's of the order of few kilohertz only, right? And communication is not over video, voice, right? It's using a special code known as the dot and dash, right? A very useful way of communication. So a lot of people consider it as a hobby to communicate over ham radio and so on, right? And also, see, if you want to do some kind of a research, right? So you first have to experiment, right? And so there is some band known as the ISM band, industrial, scientific, and medical band. So where academic institutions, right, can do a lot of experiments, or industries can do a lot of experiment and come up with newer and newer equipment and devices and so on, right? So ISM band also is unlicensed. Unlicensed means you need not pay anything. You can just start operating in that band. You can build your transmitter and receiver and operate in that band. So, so these are the frequency bands available at Wi-Fi. So sometimes you will see, right, when you connect, go to an institute or try to connect, it will say Wi-Fi 2.4. What does that mean? So this is the Wi-Fi that is operating. So Wi-Fi, this is the band at which it operates, 2.4 to 2.5 gigahertz band, right? There are 14 different channels, and each channel, just like your FM transmissions, so any communication, right? Whenever you do communication, if you have a center frequency, if you remember your digital communication or analog communication, FC, that center frequency, right? So center frequency starts from 2.4 megahertz onwards. So different center frequencies. And then there will also be a bandwidth. What is bandwidth? Upper frequency minus lower frequency is the bandwidth. Some bandwidth is going to be allocated. Okay. So there are 14 different channels. So this form of visualizing is going to be challenging. So let's switch to this view here. So 14 channels and roughly 22 megahertz bandwidth each channel, right? So there's center frequency and the bandwidth is 22 megahertz. And at any point in time, so there are going to be 3 non-overlapping channels. Okay, so 3 non-overlapping channels. So these are actually important. So what happens is when a 5G network, sorry, when a Wi-Fi is installed, right, in an organization or an institution, so you will see that along a corridor, you'll see some 2 or 3 access points, right? How will they operate simultaneously? 2 or 3 access points, right? So let's say I've installed 3 access points. So one access point will take channel 1, other access point will take channel 6 and channel 11, right? So access point 1, 2, 3. So let's say access point 1 is allocated channel 1 and access point 2 is allocated channel 2. So there's going to be interference, right? It cannot operate. So, right? So there is a significant amount of overlap between these two channels, right? So that way, so how is this channel allocation occurs? How does it happen? See, Wi-Fi or even cellular network, 5G network, we say wireless, but only the last mile is wireless. What do we mean by last mile? It is from the base station to the user is wireless. The entire background is wired connection. Okay, so we say wireless, but the world is entirely wired. Okay, so that's the interesting part, right? So wireless is only the last leg or the last mile connection is wireless. Okay, so even Wi-Fi. So when you talk about Wi-Fi, so the last part is wireless. So your mobile phone and Wi-Fi access point is wireless. You see there is an Ethernet cable that gets connected to the Wi-Fi access point. It goes to a control center. Okay, so every organization will have a control center. So in your home scenario, so your ISP, Internet Service Provider, would give you an Ethernet cable. So you plug in that Ethernet cable into your wireless access point. Okay, so you see the last leg or the last mile is always wireless, but the entire background, okay, is all wired. Your Wi-Fi access point to the Internet Service Provider is also a wired connection. From there to the gateway is all wired connection. In the case of cellular network, it's all optical wires connected, optical cables. Of course, in some cases, we use microwave communication and so on. Okay, anyway, I'll not go into those details. But this is how the Wi-Fi channels look. Okay, so there are 14 channels. At any time or any region, there is going to be 3 non-overlapping channels. Then, so recently, 5 gigahertz band also was allocated to Wi-Fi, right? So as I was mentioning, so if you go to an organization, try to connect to a Wi-Fi access point, so you will see Wi-Fi 2.4, Wi-Fi 5. So even if you buy a latest access point for your home, there are multiple. So there will be multiple antennas as well, and you will see that you will get. So you will name your access point as something. So you will get that name 2.4. Whatever is the name 5, right? So that way 2 different channels are available or 2 different bandwidths are available for Wi-Fi. So 5 gigahertz, so there are many more non-overlapping channels. And the interesting part is channel aggregation is possible, right? A 2.4 gigahertz band, so all channels were of same bandwidth, right? Roughly 20 megahertz. So here what you can do is there are so many channels. So you can combine 2 channels to get a 40 megahertz band. Right? Some applications will require 40 megahertz. Sometimes you can combine 4 different channels. So that's known as channel aggregation and get a 80 megahertz band and so on, right? So many more applications or more data rate is possible because of channel aggregation in 5 gigahertz band. Right. Okay. So for Wi-Fi, we need something that works in a distributed fashion, right? So that means, so we need a method or an access control method that works without a central controller, right? So all these schemes are ruled out. So these are all ruled out. You cannot use these in the Wi-Fi scenario, right? So these are all known as the centralized schemes. Okay, so for instance, in the case of OFDM, the resource blocks are allocated by the base station. Okay, so your mobile phone is continuously connected to the base station. So a lot of control messages keep happening. Although you might not be using your mobile phone, although you might not be doing any phone call or browsing, right? But even at this instant, your mobile phone will be communicating something to the base station at regular intervals, right? So when you are in a travel, so you switch from one base station to the another base station. So a lot of control messages are going on, right? Very short communication, but your phone is in communication with the cellular base station constantly. You might make a call or not make a call, but it is in constant communication. So the base station does all the central control here, right? But in the case of Wi-Fi, so you just come in, you can switch off Wi-Fi, okay, you can come in and go, right? So there are a lot of users. All these schemes cannot operate, okay, because you are connected for a shorter amount of time. It's a small network, so you're connected for a shorter amount of time. But you are connected to a base station for a longer amount of time. right? So you will not travel so easily out of a base station. You will remain in your home, you're connected, right? But you might be frequently moving out of the home, but still you're connected to the same base station, right? So that way, the operation method of both cellular and Wi-Fi are totally different. So all these schemes cannot work for Wi-Fi. So Wi-Fi has something known as carrier sense multiple access, right? So some of you working in the area of communication might have heard of this thing, IEEE 802.11, right? So what does this mean? So IEEE everyone knows, right? So it's the famous institution, right, for electrical and electronic engineers. So they have a lot of standards, right? So, so every standard will have a number assigned to it, and the number assigned to the Wi-Fi is 802.11, right? Of course, there are so many variations now, 11A, 11B, 11N, and so on, right? 802. But in general, 802.11, right? So similarly, the sensor networks, they have their own standards, right? So I don't remember exactly. I think it is 802.16 or something, right? So many standards are there. It's not just for Wi-Fi. So IEEE has standards for so many things, including electronics related activities, VLSI activities, and so on. Lot of standards, microwave standards, and so on, right? So 802.11 actually represents that. It's not some magical number. It's essentially they are giving some names. It's like a file name, okay, for that particular standard, okay. So what is carrier sense multiple access, right? So let's try to understand how the Wi-Fi operates. So I've taken a simple scenario where let's say there are 4 users, and let's say there is an access point, and all 4 users, let's say, are trying to download or watch live streaming, right? Or let's say download or watch something on YouTube, right? There are 4 users, right? So that means the base station, they have made request for some video or some news article and so on. So the base station has to, or there's some communication going on, right? So now, so let's start from this instant onwards, okay? What is DIFS, okay? So DIFS stands for distributed interframe spacing, okay? So just after a communication is over, all devices go into a silent mode for some amount of time. So that amount of time is known as DIFS, distributed interframe spacing. So just after this amount of time is over, they will start something known as, I'll talk about this back-off count. This is known as the back-off counter. So all 4 devices are, so someone has to communicate now, someone has to transmit. In case of cellular network, the base station decides who has to transmit. But here, everyone is on their own. Now, which user should transmit? So what they do is they do some kind of randomization, right? So every user is maintaining an internal clock, internal counter. They're counting down, okay? So let's say this user has just finished its transmission. So it will going to pick a random number, okay? So random number and start counting down. Okay, so assume that the number is from 0 to 100, will randomly pick, and in every time unit, which is of the order of millisecond, it will start counting down. So whichever user has the smallest number, let's say this user maintains the number 50, so 40, let's say 10, 20, right? So they'll start counting down. So it's counting down from 10, 9, 8, and so on. And when it reaches time 0, it will start transmitting. Okay, so you see, so it will reach, so in 10 time units or in 10 milliseconds, it's going to reach time 0. Its counter value will be time 0. It's like a clock, alarm they are maintaining. It's a timer. So they have essentially a timer. Each timer will have, each user is maintaining a different timer. Okay, so whichever timer expires, they'll get to transmit. And how the transmission occurs, they just don't go ahead and transmit the data. First is you have to have something known as the RTS signal, request to send. Okay, so a request to send signal is transmitted. Following the request to send, there is a short pause. Okay, so this is a disciplined way of talking, right? You just don't transmit the data. So after request to send, you send something known as a short interframe spacing, SIFS, they call it as, right? So in response to SIFS, you will have something known as the clear to send signal. So this is sent by the access point, right? So there is a transmitter transmits RTS, receiver transmits CTS, clear to send signal, right? It says that this is known as the handshaking, right? So you transmit and you wait for an acknowledgement signal, clear to send. Now you are ready to transmit. So again, there is a short break, and now you start transmitting the data signal, right? So the useful signal is here, right? So this is where you actually transmit the useful signal, right? Packets. It will be all in the form of data packets, right? So any big file will be broken into different small data packets, and you have to transmit many data packets to get the entire file, right? One big video, it comes in the form of data packets, okay? So then data, then again a short break, and then an acknowledgement packet is received. With that, this data packet has been received successfully, right? So again, the process repeats. You see, again, a distributed interframe spacing. Again, what happens is, you see this timer had taken value 0. Again, it will start taking a new value. Randomly, it will pick a value, right? So from 0 to 100 milliseconds, let's say. Actually, it's 0 to 32, but I'm just using for simplicity 100, okay? So it will randomly pick a number. Again, they'll start counting down. So during this time, so what this represents is, all these other users, 1, 2, and 4, they'll freeze their counter value. So let's say it was 30 here, and the timer value became 20 here after 10 milliseconds. It will keep the value at 10. So 20, it has come to 10. It will just freeze its counter. It will not reduce this timer value anymore. So again, you're going to start your counter here, right? Once an acknowledgement packet is received, you wait for some amount of time and start your counter down, right? So start counting down, right? So essentially, it's like a counter. Every user has to maintain a counter and keep counting down, right? So we have taken Wi-Fi for granted, right? But Wi-Fi technology, right? So this algorithm is very interesting. Carrier sense multiple access. You don't need any base station for this to operate, okay? So it may be inefficient, but this is a reliable way of communicating to avoid interference between different communications, right? So this will bring some kind of order across all these users, right? Who should communicate first, who should go next, and so on, right? So naturally, you're using randomness to take care of that order, right? So in this particular example, user 4's counter counts to 0, timer expires, and it starts transmitting, right? And of course, it's possible that sometimes both the users pick the same random number, okay, and their timer expires at the same time. Then both of them sends an RTS signal, request to send signal. What happens is, both of them are transmitting at the same time, right? Collision will happen. It's like, let's say two students talk at the same time. So there'll be interference, collision will occur. Then there is no clear to send signal. The RTS has to be followed by clear to send, right? Both are willing to transmit, but there is no receiver ready to receive, right? So no handshake has happened, right? So you can only transmit when a handshake occurs. RTS followed by CTS, then you are allowed to transmit, okay? So this is how the Wi-Fi operates. So it's a very interesting algorithm that goes on inside the Wi-Fi access point. Although the access point is small, but a lot of interesting things are happening there, okay? So these are some parameters, typical parameters of Wi-Fi. The slot duration, I just used 1 millisecond, but look at the slot duration. It's of the order of microseconds, okay? And back of counter size, I was telling about 100. So it's only 0 to 31 slots. So these are the length of diffs, distributed interframe spacing, 34 microseconds, SIFS 16 microseconds, length of the acknowledgement packet, okay, 256 bits, MAC header, right? So this is the CTS and RTS signals, 288 bits. And payload can be of these many number of bits, right? Of course, you need to have more data, right? So these are all acknowledgement packet is short bits, short number of bits you will use. Okay, so just to tell that the packet has been received, but actual data is carried here in the payload, right? So the actual data. So this will be of larger length. Okay, so this is just some typical parameters. With newer versions of Wi-Fi, there are more optimized values that one uses. Okay, and lot of optimization happens there. Okay, right. So we talked about what Wi-Fi uses is something known as the contention-based MAC, okay, medium access control. 5G uses schedule-based MAC, right? Now the next topic or the continuation of this is, so why did I talk about 5G and Wi-Fi? Because I want to discuss how 5G and Wi-Fi can coexist in the same band, right? The Wi-Fi used to operate in 2.4 gigahertz or 5 gigahertz now, but 5G has a dedicated bandwidth, dedicated spectrum allocated to 5G. But in 5G, there's also there's something known as unlicensed, 5G unlicensed, they call it as, right? Where 5G can also transmit in the Wi-Fi band, right? Suppose there is no Wi-Fi in some place, okay, so why should you not utilize that band, right? Unlicensed spectrum also you can utilize and get much more throughput than what you are getting with the licensed band. In addition to licensed band, you can also transmit in the unlicensed band. So that's the key idea about 5G unlicensed, right? So the question I want to address is how can 5G and Wi-Fi coexist in the same band, right? So at this juncture, I can again pause and take a couple of questions. So before I proceed further, so are there any questions? So let me just check here.
There are questions.
Okay.
During communication between multiple devices,
Yes.
how would the second, third, and fourth devices would know that the first device has finished its communication with the router? It is purely timer based, or is there any other technique?
Yeah. 1 second. Yeah. So as I was talking here, so in the case of Wi-Fi, so what will happen is the device receiver is always on. So it cannot transmit at any time, but it can receive always, right? So what happens is, so let's say this user is transmitting here, right? So all other users will be listening to this transmission. Of course, they cannot decode. Okay, so they will be listening to this transmission because they'll sense energy in the spectrum. And then acknowledgement packet is common. See, RTS, CTS packet, everyone can listen to. Once an RTS packet they listen to, they decode the RTS packet and they know that some communication is going to happen, right? Finally, after the data packet has been transmitted, an acknowledgement packet comes, right? Once they hear an acknowledgement packet, this everyone can decode. Once they listen to an acknowledgement packet, they know that communication has stopped. Now again, we can attempt transmission, right? So now everyone has equal chance to transmit again. So that's how in Wi-Fi, they know that you can now start transmitting. Okay, so I hope that was the question, right? Yeah. So is that clear? Yeah,
There is another question.
Yes.
Why is Wi-Fi still reliable and fast when compared with 5G?
No, not exactly. I mean, you cannot see Wi-Fi is reliable in your home network, okay? But when you go to public Wi-Fi, it's not so reliable, right? In a home setting, if you see, hardly 2-3 devices are connected, right? So that way, the number of devices connected to your home Wi-Fi network is very less, right? So that's why it appears to be reliable. But if you go to a different setup, so particularly conferences and so on, right? When a lot of users are there, you'll see that you cannot get, so there's a lot of contention happening, right? So Wi-Fi throughput will come down. So I'll show that graphs also. So Wi-Fi not exactly is reliable, but in a home setting, you'll see that Wi-Fi is reliable because only you and your family are connected to your home network, right? But if you think of the 5G network, lot of users are connected to 5G network, but still you are able to get 5G data, right? So that way, both networks are required, both are useful, right? But 5G essentially is more reliable. Yeah. Yeah. So difference between CDMA and CDMA methods, right? Yeah. So CDMA code division multiple access. Although military they use it, right? So military communication still uses CDMA because CDMA is highly reliable or you cannot break the code so easily. CDMA code is useful. So for very reliable communication or secretive communication, you need CDMA. So there are multiple versions of CDMA. I think CDMA methods, you mean CDMA 2000s and so on. So they're like improvements over the old methods of CDMA. CDMA 2000, what they do is the length of the code they increase. See, once you increase the length of the code, more number of codes you can generate, right? It's essentially like binary digits, right? So if I give you two binary digits, 0, 0, only 4 possibilities are there, 0, 0, 0, 1, 1, 0, 1, 1, right? If I start increasing the length of the binary digits, you can generate more number of secretive codes, okay? So in a very basic sense, so it's essentially that, okay? Yeah, so anything else? How to protect a device when it is connected to public Wi-Fi, as there is chance of attack. Yeah, so the best way to protect is whenever connected to public Wi-Fi is just to ensure that you don't log in into critical sites or so on. Okay, so any links that you don't know, of course, even in the 5G network, you are not supposed to connect to any links. Okay. So public Wi-Fi, so always there is some threat. So just for light browsing, you can use the public Wi-Fi, right? So that care you have to take, whether it's Wi-Fi or even 5G. So any unknown links, right? So you're not supposed to click. So there is some chance of attack, right? Otherwise, in general, your phone cannot be hacked so easily unless you yourself unknowingly give that permission to hack. Okay. So even public Wi-Fi, it's fine. So without your approval, hacking cannot happen. So current status 5G deployment worldwide. So even in India, it's highly deployed. So 5G in US also have been deployed, but everywhere around. So only one aspect of 5G has been deployed, which is the enhanced mobile broadband. So still the URLLC applications have not been deployed. There are few challenges because you have to see it. A lot of cost factors are involved because you want to use the existing base station. You don't want to make too many changes because you want the network to be operational, because users will not be quiet, right? See, if Airtel wants to implement a new thing, so you cannot do a lot of upgradation, right? So there's a lot of cost involved in that, right? So unless they see a lot of profit out of something, they are not going to deploy so easily. So everywhere else, so enhanced mobile broadband has been deployed. So URLLC, in some areas, possibly it's deployed, particularly in some European countries, but not to the full-fledged. So that's why researchers are talking about 5G B for beyond, 5G beyond, right? Whatever, so 5G is still incomplete. Whatever is incomplete, they want to complete it in the 5G beyond technology. Okay, so that's the current status. So everywhere it's same. Public 5G and Wi-Fi. No. Okay. Public 5G. So 5G, licensed 5G operates in that sub-gigahertz band, 3.3 gigahertz band, right? Wi-Fi operates in 2.4 gigahertz band as well as 5 gigahertz band. Right now, there is no overlap. So 5G unlicensed, which I talked about, where in addition to the existing band, you can also use the Wi-Fi band. So to give you, so best way to understand spectrum is through land, right? So you want to build a home, you will buy a piece of land, you will build a home, okay? And that's your licensed home, okay? And let's say you want to do a business in shift basis, right? So there is, let's say you want to use an office for some amount of time. So let's say there is an office space. You can also hire a office space. So someone else also can hire the same office space. Both of you can conduct business in the same place, right? So in addition to your licensed home, let's say you also have an additional office space, right? So 5G unlicensed is that, right? So Wi-Fi is not allowed to transmit in the 5G band, but 5G can transmit in the Wi-Fi band. So that is the proposal. That is still not fully deployed. 5G unlicensed, a lot of research and discussions are going on in that direction. That is a research topic, so which I am going to present in the next possibly 10 minutes or so. Okay. Okay. Yeah. So maybe I'll just proceed. I'll take up also a few more questions. So I'll very quickly go now. So I think I have last 10 minutes. So I will essentially talk. Okay, let me go to the. So I was talking. So our experimental study that we did using software-defined radios. So I'll briefly mention about that. Okay. So 5G and Wi-Fi. So suppose they want to coexist together. So already some techniques are available in literature. So one is something known as the listen before talk technique. So what happens in listen before talk is, so Wi-Fi will transmit some data. They'll carefully listen for any Wi-Fi transmissions that are going on. Okay, and then transmit whenever the channel is clear. Okay, so there'll be a clear channel assessment and so on. So whenever Wi-Fi is not transmitting, opportunistically you can try to transmit, so you can avoid collision. Okay, but the throughput is not guaranteed, right? So suppose there are a lot of users connected to Wi-Fi, they're going to continuously keep transmitting, talking with the Wi-Fi access point. So 5G network will not have a opportunity to use the unlicensed band, right? So throughput cannot be guaranteed. So another technique is the non-collaborative technique. So that is the time division multiplexing they use. So essentially what the LTE does is it is going to transmit for some amount of time or some number of frames. Each frame is of the order of, let's say, 10 milliseconds. So they transmit. So this is LTE will use these many number of frames. Then they are going to leave some number of frames blank for the Wi-Fi to transmit, right? So because otherwise, if you end up using the Wi-Fi will back off. Wi-Fi is a passive kind of a device. Whenever there is some transmission, someone is talking, Wi-Fi will just go silent. Okay. So Wi-Fi will transmit only when there is no energy in the frequency or when no other transmission is happening. Otherwise, Wi-Fi will stay quiet if some other transmission is going on, right? So Wi-Fi is a pessimistic kind of a device, right? So LTE can, so that means, so LTE has to ensure, LTE is like a big brother or 5G is like a big brother who is trying to ensure that Wi-Fi users also will get some amount of throughput, right? So some number of frames are left blank for Wi-Fi to transmit. So these are the transmit opportunities for Wi-Fi, right? So this way, there can be some guaranteed throughput for LTE and both Wi-Fi, but there is some possible collision with Wi-Fi, right? So that has to be taken care. So what we are going to do, so we have formulated a proposal. Essentially, the time will be split into frames like this. So frame 1, frame 2, frame 3, and so on. And what happens is within each frame, LTE will be on for some amount of time, LTE or 5G. So I use interchangeably. 5G is going to transmit for some amount of time, and then Wi-Fi is going to transmit for, the Wi-Fi is going to leave, sorry, 5G is going to leave this amount of time for Wi-Fi to transmit, right? So this is known as the duty cycling approach. So where LTE or 5G is going to switch between on and off mode, right? So on state, 5G transmission, off state, opportunities for Wi-Fi to transmit, okay? So you have to take care of what happens, collisions, right? So when LTE switches on, already a Wi-Fi packet might be being in transmission, so it can collide with that Wi-Fi packet, right? So collisions will happen. So you have to ensure, and also short off time because of short off time, there is not going to be much throughput for Wi-Fi, right? So some kind of optimization is required here. So what we did was we built a small test bed to understand the throughput study. So essentially, these are the key components of our test bed. So USRP, this is the software-defined radios, more popular term. So USRP is the Ethos Research term. So they are the software-defined radios developed by Ethos Research. So USRP stands for Universal Software Radio Peripherals. There are different versions. So B210 is what we have in our lab. We also have the N series version, network series. So this is essentially, so we have one USRP device connected to a server here, which is a desktop. It could be a laptop also. So another USRP. So one will act like the transmitter, the other will act like the receiver. Okay. And then, so we also have the Arista net. So we got some Wi-Fi access point also. So these are the Arista network access points. So we can program these access points, right? So the power transmission, range of the access points, everything can be, we can vary software, using software, we can vary, okay? And these are some technical points. I'll not talk about this, but only GNU radio is something I'm going to talk about in a while. Yeah, what is USRP? Universal Software Radio Peripheral. So it's essentially a DSP, FPGA-based device. Okay, so it's very simple. So the USB port through which you can program this. So there is an FPGA. So this is the motherboard. So digital to analog converter and an ADC, right? So then there is an RF front end, so which is essentially the up converter, down converter modules you will have. Then there is a transmitter antenna and a receiver module also, right? So this is just a piece of hardware, right? Now, why do you call it a software-defined radio, right? So using software, you can program this hardware to behave in any fashion, right? So you can program to receive whatever signals you want, right? You can program it to be a mobile phone, right? So a lot of features are there. So a lot of experimentation can happen using the same device, right? So in one round of experiment, you can program it to be a transmitter. In another round of experiment, you can program it to be a receiver and so on, right? Your mobile phone is not software defined to a great extent, right? Your mobile phone remains as a mobile phone, right? You cannot program it to be something else, right? But USRP, that advantage is there and very useful for research activities, right? And also for deploying some applications in practice, right? And how do you program this? So there is an open source application known as the GNU radio, using which you can use a C programs, a lot of applications available. So using which you can program this hardware device, right? So combination. So this is the GNU radio. So this will be in your laptop or PC. Using an USB connector, you can connect to your USRP device, and then you can just program it. Okay. So this is how the USRP. So this is the USRP module that I was talking about. So this is the DSP FPGA kit that we have. So this is the Wi-Fi access point. So you see this is the receiver module. So this USRP is programmed to be the transmitter connected here. So this is connected here. So what we are essentially doing is we are allowing the transmitter. So here, so some transmission is happening. So this is the transmitting some message to the receiver. Okay, so some file is being transmitted here. Simultaneously, Wi-Fi also is trying to transmit some file to a mobile phone. Okay, so that's what is happening here. And here, so this is something about OFDM transmitter and receiver. So this is a bit technical. So I'll skip this in the interest of time. And I'll mainly go through some performance things. Okay, so these are, so in GNU radio, you will be able to find these things. You essentially have to fine tune. So you see GNU radio, you have to drop and drag. So drag and drop different modules. Okay, so a lot of communication modules will be available. So you have to build up this OFDM transmitter or receiver. Okay. Now these are some experimental setup modules. So what we did is we are transmitting a video file, and we are trying to understand the performance of 5G in the presence of Wi-Fi, right? So performance in terms of peak SNR and also in terms of SSIM, structural similarity index metric, which is essentially like, so I'm transmitting a video files. I want to see how many frames are matching with the transmitted file. Okay, so that's essentially SSIM metric. Okay. And I'm varying the duty cycle. So as I vary increased duty cycle, so that means, see 90% of, so 90 means 90% of the time LTE is on, only 10% for Wi-Fi, right? 50 means 50% of the time LTE is on, only 50% for Wi-Fi, right? So duty cycle will tell how much time 5G is on, how much time Wi-Fi is on, and so on, right? So this is essentially some snapshots of the experiments there. And these are some Wi-Fi standards. What happens to Wi-Fi throughput? The Wi-Fi throughput, of course, is going to decrease, right? Here 90 means 5G is transmitting for 90% of the time. Only 10% of the time is available for Wi-Fi. So definitely its throughput is going to drop. So we did some experiment with TCP and UDP, and also what happens to the Wi-Fi throughput as the gain of the LTE transmissions is increased, right? As LTE transmission becomes more powerful, so you'll see that the Wi-Fi throughput is also going to drop. Okay, so some technical experiments we did, and finally, this is the key part. So what we understood is for peaceful coexistence of 5G and Wi-Fi, duty cycling ratio is expected to be of the order of 20 to 40%, right? The Wi-Fi also should get benefit, so it should be a win-win situation for both. So LTE should use only 20 to 40% of the time in the unlicensed band. Remaining 60 to 80% of the time should be for Wi-Fi, right? And also the transmit gain should not be too much. So it should be of the order of only 65 dB. So then both will benefit, both 5G and Wi-Fi will benefit. So essentially the thing is, so this is useful for small cell 5G, right? Or we are talking about 5G in the millimeter wave, right? So where it's small cell, order of small cell, right? So only in indoor setting, this is going to be applicable, this study. Okay, right. So with this, I will end. So these are some standard references. So I've shared the slides with Madam, so you can get the slides. So if you want to get a greater understanding of communication, so there are a lot of standard textbooks. So for Wi-Fi is something I talked about this textbook. So wireless networking. So Professor Anurag Kumar is from IAC. So he was my PhD supervisor. Professor Manjunath is from IIT Bombay. Professor Joy Kuri is also from IAC, right? And these are foreign authors. Professor Upamanyu Madhav from UC Santa Barbara. Okay. So then there are also some. So this is something I didn't talk about, optimization. So game theory, some people might have heard of game theory, a very useful modeling tool. In some other context, I can present at a later time. Then also learning, right? Reinforcement learning. People talk about machine learning. So there's a more fundamental form of learning known as reinforcement learning. So we have done some work in that direction also. And these are some references. And our, so the test bed that I talked about is essentially this paper. So it was presented at IEEE conference, which was held at Gandhinagar. So this is an experimental study using GNU radio and USRPs. Okay. Yeah. So with this, I'll stop. So I can take up few questions. So yeah. So if there are any questions, so let me see.
There is a question. For multiple devices, does it require multiple USRPs? If so, how about its hardware cost, it seems?
Yeah, so multiple, okay, so here is the thing. So multiple devices. So for instance, we wanted a LTE transmitter and receiver. So we had to go for two devices here, two USRP, right? So this USRP, the cost is of the range of, so this was few years back, something of the range of 1,10,000 or something. So this USRP device, okay? So this is the basic version. Then there are high-end versions also, which is of the order of 5 lakhs also, right? But if you want but USRP devices, much lower prices also are there, of the order of 20,000 also. But their operational band may not be too much. But for low-scale experiment, you can always go for that. So there are low-cost USRP or low-cost SDRs, software-defined radios. USRP is a term adopted by the Ethos Research, which is a company which makes these USRP devices, which was absorbed by NI, right? National Instruments. Okay, so NI, big company, absorbed by them. So that's the cost of these USRP devices. Yeah. Yeah. What are the other questions? Let me see the chat box. Yeah.
Dear participants, if anyone has any queries, kindly post it. Or else unmute yourself and ask.
Yeah, you can ask directly. Multiple devices. Hardware cost I mentioned. So I think there's one more here. CSMA and CDMA. Carrier, yeah. So huge. So, okay, CSMA is something used by the Wi-Fi. Carrier sends multiple access. That's a distributed multiple access technique. CDMA is used by the cellular base station. See, cellular and Wi-Fi, two different things. Okay. Cellular base station are owned by big companies, Airtel, Jio, and so on. Wi-Fi, you own your Wi-Fi network, right? Or Wi-Fi in IIT Tirupati is owned by IIT Tirupati, right? And there you are not going to use CDMA, all those things will fail. You use CSMA, carrier sense multiple access. It's a distributed multiple access mechanism. CDMA is a centralized multiple access mechanism. You need a central controller. You need a master to control the entire class. You need a teacher to control. Here, the students are for themselves. They have to control themselves, right? So this algorithm is for that. They have to do a group study here. They are on their own. Here, you need a master to control all the students. So that's the key difference. So this is more efficient. This is less efficient, but this doesn't require a master. Okay, so the cost is going to be less here. Okay, so that's the key thing. Okay. Yeah. So any more questions? So
Any more questions from the participants, or shall we wind up? Sir, shall we wind up, sir?
yeah, sure. Thank you again. So I'm just trying to
We extended our heartfelt gratitude to Dr. KP Naveen sir for delivering an insightful session on wireless communications for embedded systems in Industry 5.0. Your comprehensive coverage of topics including the evolution of network generations, ultra reliable low latency communication, technical specifications of 5G networks, multiple access control mechanisms, various frequency bands, Wi-Fi technology, IEEE 802.11 CSMA, USRP devices, etc. And very thankful for Dr. Naveen sir for sharing your expertise and making this session highly engaging and informative. Your guidance will undoubtedly inspire us to explore these cutting edge technologies further, sir. Thank you, sir.
Yeah, thank you all. So thanks again for inviting. So thanks to all the participants. So I'm glad that I was able to share some knowledge with you. Okay, yeah. So thank you all.
Thank you, sir.
Thank you, madam. Thank you so much.
Thank you, sir. Naveen, sir.
Yeah, thank you, madam. Thank you so much. Yeah. So I can sign out, right? I'll sign out.
Yes, sir. Yes, sir. Thank you.
Thank you.
The feedback link is posted in chat box.